Walailak University is located in Thasala, Nakorn Si Thammarat, a major city of southern Thailand. The province has many natural wonders and beautiful beaches all along the coast, and is in the same region as the popular beaches of Koh Samui and Phuket. The campus is surrounded by the beautiful and large greenery of Khao Luang National Park. Walailak University presents a fine example of the feng shui concept of water, land and mountains combination. With the direction set by Professor Dr. Sombat Thamrong Thanyawong, our president since July 2016, the university has stepped into an era of change, focusing on high quality, both in teaching, learning and research. Over 90% of the students who graduate from Walailak University pass professional examinations in their first attempt, one of the best records in the country. Walailak University was assessed by the Office of the Higher Education Commission of Thailand in 2019 and awarded a score of 4.8 out of 5, which is among the highest in the country. Crucial items of the ranking included quality of graduates, research and publication, social engagement, promotion of art and culture, and management. In addition, academic ranks have nearly doubled in the last 4 years. The rate of employment among graduates is 98%. Something that we at Walailak University are very proud of. To achieve high quality and internationally recognized learning outcomes, Walailak University incorporates the UK Professional Standards Framework or UK PSF in all her teaching. High-level student learning is of great importance. About 60% of our teaching staff have been awarded fellowships from the UK-based Advanced Higher Education. As part of Walailak University's internationalization efforts and to prepare for our graduates for high-level and international job opportunities, English language proficiency is emphasized. There are more than 30 international educators dedicated to first-year English language teaching alone at the university. Smart facilities such as smart classrooms, smart laboratories, smart mobility, and smart security are in place so that the students can truly enjoy their university life and develop the various skills necessary for their future careers. Study at Walailak University is active, engaging, and fun. Walailak University is a comprehensive research university with 3 main academic areas: health sciences, science and technology, and social sciences, with 42 programs across 14 schools and 3 international colleges, plus a number of international courses. Walailak University cares deeply about her staff and student health. The university provides modern high-standard sports facilities, including swimming pools, a fitness center, and other sports amenities. Walailak University prides herself on being a leading comprehensive research university committed to academic excellence. The university operates 21 centers of research excellence that drive high-level research and education and academic careers and academic services that support Thailand's technology policy or Thailand 4.0. Her achievements are reflected in the SIMAGO institutions rankings. Walailak University's innovation and research publications rankings have been among the highest both in Asia and in Thailand. In addition, Nature Index ranks Walailak University among the top in Thailand in physical sciences. Also, Walailak University regularly produces world-class publications in ISCIR Scopus Index journals. Internationally rated and cited research publications have increased dramatically under Professor Dr. Sombat's leadership, and Walailak University is increasingly recognized for its active research environment. Social engagement projects that translate research findings and innovations into practice for the benefit of the community are another hallmark of Walailak University. Entrepreneurial spirit is much valued at Walailak University. Students can enjoy co-working spaces with the private sector right here at the university's Science and Technology Park. With a pristine location surrounded by greenery, Walailak University is a natural location for a botanic garden. Initiated by the schools of pharmacy, Walailak University features one of the most beautiful herbal gardens in Thailand. Not only is this garden beneficial to the students of the School of Pharmacy and Applied Thai Traditional Medicine, it is also a place where the public can visit and enjoy. Walailak University has one of the most treasured 216 hectares botanic garden, featuring a diverse tropical plants. It is also a popular camping ground for the university students and staff and the public. And this is where a natural history museum is being constructed. The museum is an initiative of Her Royal Highness Princess Mahachakri Sirithawan. With combined land and man-made lakes of 48 hectares, Walailak Park is a famous place for recreation, not only for students and staff but also for the public. Sitting at the park's deck, watching a sunset against Khao Luang Mountains in the evening is a pleasure enjoyed by many. Walailak University plays a very significant role in addressing the country's healthcare needs, especially in southern Thailand. The University Medical Center, constructed on 65 hectares and with 750 beds, and the most advanced medical technology will be operational starting in 2021, serving up to 500,000 patients annually. The university is committed to providing education opportunities for all. The university seeks to excel in research and innovations. The university's mission to produce graduates that are both professionally competent and morally sound is uncompromising, consistent with the vision to be an institution of good governance, a source of knowledge for critical problems facing the nation, to unfailingly address community needs, and to strive for international recognition for excellence. A university where young people can embrace their dreams, a university that challenges itself to promote harmony and solve global problems. Change never stops. We are changing. We are a university of quality. This is a land of glory for all.
Good morning, Professor Barros there.
Good morning. Are you listening me? Are you listening my voice?
Yeah.
Okay.
Can hear you.
Excellent. Okay. So I'm ready. I don't know if you want that I share my monitor, in order to see if you see my presentation. please guide me in order how to do, okay?
Right. I would like to welcome you to the ISCIR. This is the third event that we organized this year, and this is day 2. So we just complete day 1 yesterday, and sorry for the Thai participant that we have to organize in the right time that fit with the European and UK time as well. So today we have 5 keynotes and about 6 invited theme speakers. And also the first keynote will be Professor Joachim Barros. We have Chair Professor Nakorn and Dr. Muntian. So I pass this to Professor Nakorn, please.
Thank you, Professor Thanongsak. It's my pleasure to be the chair for the keynote in the afternoon now. And the topics for today will be the combining proper materials and numerical tools for the development of innovative and sustainable construction system, the case of P-slab tech. The keynote speaker, he is a full professor of the Department of Civil Engineering of Minho University. He's the director of the PhD in Civil Engineering. He's the header of the Structural Composite Group. He's a fellow of ACI. He's an active member of several ACI. He's a FIV and RIIE-WU technical committees. His research interests include structural strengthening, composite materials, fiber reinforced concrete, and development of material constitutive models, and their implementation in software based on the finite element method. He's the author of more than 800 publications. He's a co-founder of FEMIX, FEM-based computer program, and inventor of several national and international patents. He participated in 37 research projects, supervisor of 7 postdoc, 41 PhD, and 33 Master of Science. Please welcome Professor Joachim Barros from University of Minho, Portugal, please.
Okay, thank you, Professor Nakorn, for the nice introduction. It is my pleasure to participate in this event. So I will share my monitor in order that verify if you see. Do you see the presentation?
Oh, clear.
Yes.
It's clear. Thank you.
Yes.
Okay, okay. So, well, what I'm presenting today is not my exclusive work, it's the work of a team. So this is the, I should say, an overview of the research that we conducted for the developing of and use of mainly 2 materials, as I will have the opportunity to show, and involved 3 institutions. So 2 private companies, Civitest, Serralharia Cunha, and also the University of Minho. And so, as you can understand, this mobilized several people, and I'm trying to resume the fundamental aspects. So, okay. So I'm presenting presenting the motivation, the material and structural concept, modeling and design, and the conclusions. So, well, what is the main motivation? In fact, is to combine materials that have complementary materials. Sometimes I indicate to marry materials. And the idea to develop sustainable construction systems that are competitive, that they accomplish the service and the ultimate limit state conditions when we design. And also to verify, to explore the potentialities of producing this construction system by robotized prefabrication industry. So also to minimize the material, the labor resources, transportations, and also to minimize accidents. And we have also the aim to assure better quality control, because if we produce this in a robotized prefabrication industry, so in fact, we have the possibility to assure better quality. Also to have the possibility of introducing self-monitoring capabilities during the production. And and eliminate the time of preparing and applying conventional flexural and shear reinforcements by at the same time ensuring ductile failure modes. But obviously we want that these systems present ductile failure modes. And in this way, we develop a slab system, a prefabricated slab system with the name of the nickname of Pre-Slab-Tech, and combining fiber reinforced concrete and girders, longitudinal girders made by cold formed steel sheets with engineered openings in their waves in order to have a good connection between the fiber reinforced concrete and this longitudinal steel girders. So we can see here a schematic representation. So we have, this is a cross section where we have this part is made by the fiber reinforced concrete. So we see here, this is a cross section, okay, a part. This is fiber reinforced concrete. We have here the steel girders with engineered openings filled, as you see here, by fiber reinforced concrete. We have this transversal thin wall tubular steel elements in order to increase the transversal stiffness. And we have this extruded polystyrene blocks for serving for molds when we cast the deck, and also to increase the thermal insulation. And finally, we can also add in the bottom some acoustic and fire insulation. So is another perspective. We have here, as we see, the optimized shape profiles made by cold formed steel sheets. So this is the extruded polystyrene material, and finally, this is the fiber reinforced concrete that is filled the total part, composed, introducing the deck as well as filling the girders. So this is a patent that we register, and we see another view. So do you see here? So there is the longitudinal view of the longitudinal girders. Where we have these openings, and since the fiber reinforced concrete can flow through the openings, so we were able to provide to this system a very high shear capacity. As you will see, it was not able to introduce a shear failure. So the shear capacity of the system is very, very high. So in reality, this system was, I should say, proposed or was invented to solve a practical problem. So the Civitas company was invited by a client to develop a very lightweight system, very fast to execute, due to the problems of where this, to restriction in Gibraltar country, and then in reality, this system was designed for attaining the requisites by this client. So this is a component where we see the supporting. So we have like a frame composed, the reaction frame is composed by steel profiles, and this is the slab, and this is a typical connections between the slabs and the steel frame composing this building. So what are the advantages? To ensure the construction of floors for residential, commercial, and industrial buildings up to 12 meters span, with the lowest ratio between the self-weight and the flexural stiffness, and without the occurrence of a shear failure. So lifting equipment of relatively low load capacity, it can integrate in its prefabrication the components that assure the required structural, thermal, acoustic, and fire protection performance. It can be partially or integrally prefabricated with a high export potential. We don't need shoring, so which is very nice for faster construction. And well, in the faster execution of pavements of high quality. This is the relevant advantage. So we started to execute some small prototypes, beam elements, in order to explore the concept. So this is a fiber reinforced concrete. This is the profile that has openings, and when we cast, so due to the self-compacting nature of fiber reinforced concrete, so the concrete, the FRC flows through the openings of the steel, and then we have this type of designated shear connectors. As you see here, this is a low deflection, so we have a very, very ductile behavior for this system. So we start characterizing the properties of the fiber reinforced concrete. So it has about 60 megapascal at the end of 28 days. And we characterize the post-cracking tensile capacity of the FRC. So according to the EN recommendation, so we obtain a flexural stress, equivalent flexural stress of about 7 megapascal for 0.5 millimeter, and for 2.5 millimeter, it is also close to 7 megapascal. So it is like a plateau flexural tensile capacity of about 7 megapascal, which is very good, or is sufficient for our aim. So, and in reality, we need to have these properties in order to define the post-cracking tensile capacity of the FRC when we are designing this slab system. So here, so we tested almost real scale prototypes in bending, in shear, and we also execute a creep test with, as indicated, real size prototypes, or almost real size, and also dynamic tests. So in this is the one configuration, or first configuration for the flexural test. So it's designated B4400 because it's a span length of 440. So it was tested in 4-point load. And we have here a photo of this test. We have a short movie, a video, or a moment. So we can see, this is before the video. So this is yet another configuration for the flexural test. With is a 3-point loading configuration. And where, as you see here, we install strain gauge to monitoring the strains, the compressive strains in the FRC, and we bond strain gauge in the bottom in steel profile to monitoring the strain in the steel. And we also applied rosettes in order to evaluate the principal strains, and consequently to estimate the maximum compressive stress, because the maximum compressive stress can give us an idea about how close to the shear failure we are, and also obviously to estimate the shear deformation. So this is now the movie. So it's a very short. I don't know if you listen or not.
No, there is no sound, Professor.
No sound.
But
okay,
you can tell us. No, you
okay.
can tell us more or less.
Okay, good. Because this is a representative, is a schematic representation of the production. So do you see here? So we are casting, okay, and now we are going to laboratory. So this is laboratory of CV test. So in fact, the tests were executed in CV test, and it is being prepared, the prototype. So so now we see the execution of the slab. So we produce these prototypes manually, but as I indicate, the idea is to transform or to use new prefabrication or use a new prefabrication industry for producing this type of slabs. So we see the load versus deflection. So the green is uncracked stage. Now the blue, we are in post-cracking stage. So, but we see that in post-cracking stage, we have a very small loss of flexural stiffness, which is very nice. So, so here we have the yield initiation at this point. But as you see, so we can continue to have a relatively large stiffness. And now, so it is yielded. So the load carrying capacity when the longitudinal profile start yielding, so is equivalent to a live load of 34 kilonewtons per square meter, which is obviously too high. This means that this the flexural, the load carrying capacity of this prototype can support a larger span length. In this case, the span length is 4.4, but take in consideration these results. So in fact, we can apply this prototype in applications of larger span length. So when we handed the test, so the load carrier, the equivalent uniform distributed loads is 44, which is huge for what we want. So this is the final aspects. So we see here the fiber reinforced concrete that goes through the openings in the longitudinal girders and serves as a shear connectors. So we can see here, so the force deflection for this 4 loading configuration and for the 3 loading configuration. And the dead weight of this prototype is 210 kilograms per square meter. And we applied 0.08 cubic meters per square meter of fiber reinforced concrete. And the content of steel in the form of cold form steel profiles is about 18 kilograms per square meter. As I indicated, so for instance, in this example, when the test was handed, so it is possible, or this prototype can support an equivalent distributed load of 44 kilonewtons square meter, which is obviously much higher than the values that we use for residential and even commercial. Well, we, as indicated, so we in the rosettes, if you remember, in these rosettes that we install here, so we measure the strains. So we measure the strains here in these 3 sensors, and from these 3 sensors we obtain the maximum and minimum principal strains and their inclination. And from the compressive, so use positive and negative values in our case represent respectively tension, positive tension, and negative compression. And for the maximum compressive strains, and using the parabola rectangular diagram, we estimate the compressive stress installed in this in the prototypes that we are testing. So we can see here for the prototype that was testing bending with a 4 load configuration. So this is the force versus compressive strain. And we see that the strain gauge installed in the 2 longitudinal girders, as well as in the deck has only 40 millimeter, 40 millimeter. So we realize that the strains are almost equal, which means that we can use a relatively simple design approach, assuming like this, like a T-beam, which is very convenient for design. And as we see here, the compressive strains was a maximum about 1.6 per mile, and consequently, we did not attain at this stage the peak compressive stress of this FRC. In the case where the test was conducting 3-point load configuration, so well, the strains are still in a linear stage because the maximum compressive strain is very small. So this is the strains that we measured 200 millimeter from the loaded section. So it is installed here and here. In this case, the strains are measured in the loaded section. So when we are measuring the strains in the steel, for instance, in the flexural test, we realize that in fact we have exceeded significantly the heel strain of the steel that we use for producing the girders. So we see clearly here. But when we interrupt the test for the case of B240, for the case where we adopted a 3-point configuration, well, the steel is 1.6, but 1.6 is almost just initializing the yield strain in the girder. So in using the data that we collected from the rosettes, so we have 2 rosettes. So this one that we designated by Nabla is close to the loaded section, the central section, and we see here that the maximum principal strains was about 2 per mile. So this is a compressive strain, and the maximum tensile stress is exceeding 50 per mile. So consequently, this means that well, in fact, since the maximum compressive strain is less than the crushing strain, this means that we are not yet, we did not attain the stage where a shear failure can be formed in this region. So we see also that this is the variation of the principal strains, So we see that the angle is almost constant, close to 40. So the 40 degrees is constant. And when we attain the yield initiation of the steel using the girders, so the angle started decreasing and approaching to 0, which means that the plastic hinge is spreading in this region, and consequently we are in fact obtaining a flexural failure mode, not a shear failure mode. So when in the case of shear, so we see here, so this is the configuration. So we have the loads, the support and the support. So we have the strain gauge in the steel in the bottom, in the top, and and we see here the force deflection. So linear elastic, crack starts initialize here, and then so this is a crack is progressing, but we never attain the shear capacity. So in fact, it was necessary to interrupt the test because we attained the maximum load carrying capacity of the reaction frame, that was 500 kilonewtons. So we stopped because it was not possible to continue. And we, at this stage, we had no shear failure. So for the other configuration, for the other shear test configuration, that this one with a smaller shear span, we see here that in fact we start attaining the yield initiation on the longitudinal reinforcement. In conclusion, we were obliged again to interrupt this test because we attained the load carrying capacity of the reaction frame, and even in this case we did not have any sign of shear failure. So when we analyze the relationship between the force and the compressive strain in this shear test. So in the top, as you can see, so in reality, the strains, the compressive strains are relatively small. Look, the maximum here is like about 0.5, so the 0.5 per mile. So in the other test, in this other configuration of shear test, also the maximum, the maximum compressive strains was much smaller than the crushing strain of the fiberglass concrete. So in terms of the steel strains, so we can see here also we are again analyzing the strains in these two shear in these two prototypes testing shear, and we see here that in fact the maximum strain that was installed in this strain gauge, look for this maximum, has attained the yield initiation. So which means that, well, if we are able to continue to apply more load, we obtain a flexural failure mode, not a shear failure mode. Okay, so based also on the principal strains that we measure in the rosettes, again, we realize that the maximum strains, maximum compressive strains was relatively small, and consequently, we are not, so we don't have any sign of the possibility to form a shear failure in this system. This is the main conclusion that, and also in the other shear test, so in this configuration, we obtain the same conclusions. So in terms of moment curvature, so in fact, since we have the strain, look here, strain in section, strain in the strain in strain gauge 1 and 3, we can obtain the moment curvature in this section. We using the strain in strain gauge 2 and 4, we can obtain the moment curvature in this section. And well, using this type of approach, we obtain the moment curvature. And we see here that in the prototype that was tested in under 4-point load configuration, so this is all of them, and this is typical to all tested specimens. So the moment curvature was almost similar up to here. The only deviation, the only difference is in the S18. So this is the test, the shear test. And why? Because in this case we have the larger contribution of the formation contribution due to shear, and consequently we have this higher curvature. This is the green color that we obtain in this prototype. But apart this, so we see here the moment curvature is linear elastic, elastocrack stage with some loss of flexural stiffness, and then the yield initiation. So and using this moment curvature, or we use this moment curvature relationship for our modeling purposes. So we also execute creep tests. So we see here, so we adopted, we apply a load corresponding to a quasi-permanent combination according to Aero codes, where for live load, it is multiplied by the factor 0.3. So the self-weight of the slab is 2.2. The flooring partitions, we assume for building a value that is 2.85. So the imposed loads on the residential floors, we adopted 2 kilonewtons, and consequently, the load that we applied was about 2.5 kilonewtons per square meter. So we see the displacements measured during the loading. So we apply the loading in 4 phases. So, so in this up to 20 minutes, we apply a certain part of the load. So this is the first phase. We see an increment of the displacement. So we apply between 20 and 30 minutes, more or less, another increment of load, and we see also an increment of displacement. And after 40 minutes, we have all the loads applied, and we start measuring the deflection at a long time. So we have the instantaneous deflection, and then we start measuring the long-term deflection. We also realize that due to the temperature variation inside of laboratory, we have a dependency of the variation of the displacements on the temperature. And we monitorize this, and then we correct it, the effect of the temperature on the displacement. And we see the displacements along the time. And well, the creep coefficient, that is the ratio between the deflection at the long term, so all the accumulated deflection, minus the initial, the instantaneous deflection, divided by the instantaneous deflection. And well, we obtain a value, this creep coefficient of 0.13 at the end of 100 days when the load was applied, when the prototype has an age of 65 days. So we apply this load when the prototype or the concrete of the prototype has 65 days of age. Which is 0.13 is reality a very small value compared to the value recommended by the Error Code. This is why it's necessary to do more research in this domain to adapt the formulation for this type of prototype. So we also executed dynamic tests. So this is and we estimated we performed the model analysis with our software, FEMIX software. This is FEMIX includes a large library of type of finite elements, set of point, line, and surface nonlinear springs to model diverse contact conditions, several types of interface finite elements. We have embedded cables to simulate the reinforcements, also specially embedded finite elements to simulate fiber reinforced concrete, static and dynamic analysis with material and nonlinear behavior, and the time-dependent phenomena like concrete, so maturation, including creep and shrinkage. It includes the Newton-Raphson method, arc length techniques, and path-dependent and dependent algorithm, and also direct and preconditioned Poisson gradient methods. I'm listening a lot of voice. Can I? Oh, okay. So we have a pre and post-processing use GID to post-process results. And we see here the model analysis of FEMIX. And we see here that it was estimated also the first frequency was about 17 hertz that we measure experimentally, and FEMIX it was about 89 or so for the first mode or for the mode shape for the first frequencies, which is quite close. So we also estimated the damping coefficient for this system. It was 0.69%, and we realized. So the main conclusion is that well, in normal situations, under ambient vibration conditions, a transient is not expected to experience any uncomfortable level of acceleration, regardless of the natural frequency of vibration of the structure. So I don't have time to describe in detail this test. And finally, so we executed a software based on the matrix displacement methods that combine where we discretize the structure in elements and with the 3 degrees of freedom. In reality, it's 2 degrees of freedom, only vertical and rotation in each node. And due to the openings, we evaluate the moment curvature relationship in each possible cross sections that we have along the elements, take in consideration the openings. And we also consider well, the contribution not only of the FRC, but also of the steel profile for the shear capacity. So we use the moment curvature relationship for extracting the flexural stiffness. And this flexural stiffness is introducing the stiffness matrix of each element, and by assembling, we obtain the stiffness matrix of the structure. So we realize that this very simple approach is capable to capture the moment curvature that we register experimentally. This is numerical, this is experimental, the black is experimental, and also using this approach, we estimate the force deflection that we are comparing, so the numerical and the experimental. Numerical, after yield initiation, we have a plateau. Why? Because in this case, when we attain the flexural capacity in each element, we assume that the tangent flexural stiffness is null. And since it is null, it is formed a plastic hinge. Obviously, it is possible to introduce some hardening, and consequently, you can simulate this. But for design purposes, this is totally sufficient. So we develop an interface for design purpose, where the design defines the length of the slab, so the load conditions, and then the software evaluates or find what is the most economic solution for using the press lab tech concept in order to propose to design well, the most economic and most efficient, accomplishing the service and ultimate mid states. So finally, we executed a real prototype, as we see here. So this is a real prototype where we have the press lab tech. This is nowadays an open laboratory where we are performing thermal and acoustic tests and also dynamics. And finally, we are exploring this concept for increasing the span length. Though now we are testing the prototypes with 12 meters span length, and this is the first test, the creep test, and that's it, because the conclusions is not necessary, because it's a resume of what you explain, and I prefer to give some minutes for discussion. Okay, many thanks. Thank you.
Thank you very much, Professor. Very nice presentations. We may have a few questions, please. We're running out of time now. Please, if any audience have questions.
I have a question.
Okay.
Thank you, Reis.
Hi, Joachim. Good to see you.
Good, thank you.
I thank you for the nice presentation as well. I think at the beginning you mentioned that the idea was to make this sort of prefabricated elements. Is that correct, or are you planning to cast it on site?
No, this is for prefabrication, and the company, one of the associate company, that is Serralheria Cunha, so his plan to produce the steel profiles in a robotized line. So the idea, so now we are trying, or we are in negotiation with the companies with the desire or with the technical capacity to produce this system in a robotized line, prefabrication line. This is the idea.
Yeah. So you're basically taking like these pieces of slabs to the site. Is that the idea?
Yes.
And then practically, how are you going to put together all the pieces on the floor system? Because I mean, a floor system should be.
This is we see here. Do you see here?
Yeah.
Do you see here? So this is,
yes.
Imagine this steel profile is part of the frame, the steel frame. And then, so we have, this is the press lab tech, this is another press lab tech, and this is the joint between them. So we only cast this part in job site. This is fiber concrete, and then it is connected. We have even here the resilience. Yes, but it's very small.
Yeah. So you still need to cast some concrete anyway.
Yes,
on site,
but it's very small.
But it's
But
a
it is,
relatively small amount. Yeah.
yeah. But this we have nowadays. We are studying the possibility to have to do not or to be not necessary to apply this. But we are still investigating this connection.
Okay. Yeah.
Thank you.
Okay, that's good. Yeah. Thank you very much.
Okay, we have Professor Mauricio. You raise your hand. Go ahead.
Yes, hi. Good morning, everyone. Oh, good afternoon, I should say. Good morning, Joaquin. It's morning there.
Hey, good morning, Mauricio.
Excellent presentation. I like the idea. I just had a curiosity from the practical point of view. Are these coliform sections punched, meaning the holes in the section, are they punched or laser cut?
Punch?
Are they made before they are bent?
Are made, excuse me, I'm not listening very well your last word. Are they?
Yeah, what if the holes are punched?
No.
Or they're laser cut?
A laser cut. So this is a laser cut, and it is executed during the production of the cold steel sheet. So they produce and cut simultaneously. They give the configuration.
And then bend them to shape.
Executing. Exactly.
Okay.
And we have explored several configurations in order to have the maximum efficiency. So for instance, nowadays we are using circular because it's much more simple, and we realize that we avoid stress concentration in these zones.
Yeah. Okay. Yeah, thank you. Very interesting.
Thank you, Mauricio.
There should be more questions, but we are running out of time, Professor Barros.
Okay, thank you. Thank you. It was a pleasure.
Can you mention a bit on the FRC, property that you are using? Can you tell some idea?
So, yes. So what happened is that we made so we execute preliminary tests, as I indicated, and then due to this preliminary test, we use the software, the FEMIX, in order to estimate what should be the post-cracking tensile capacity of this FRC and also the compressive stress for exploring or mobilizing the full tensile capacity of this steel profile. So this means that we, as I indicated in the beginning, we married the materials. We put FRC with the properties sufficient in order to extract all the potential of the steel. And this is why we realized that we need a compressive strength about 45-50 megapascal in compression, and the post-cracking tensile capacity or a flexural stress crack width, flexural stress for a crack width of 0.5 and 2.5 around 7 megapascal. So, and consequently, we designed this fiber-reinforced concrete.
Thank you very much. So I think we come to the conclusion of the first keynote for today. Thank you, Professor.
Thank you.
For your very nice presentation.
It was a pleasure.
Thank you very much. Thank you.
Thank you for Professor Barros. Before we move to the next keynote, I would like you to see my one of my best friends from USA, and he also want to join us for the group photos. So could you please see my friends and turn on your camera for the group photo, please. Hello, Mauricio. Carlos, can you please stop sharing your screen, please? And ladies.
Okay.
Can you
at a moment
on your camera?
Okay.
I just come so far from USA today.
Okay. Stop sharing. Stop. I suppose I stopped sharing. No.
We can still see your.
Can you stop sharing there?
Okay.
Okay. Okay. 1, 2, 3. Cheers. Okay. For the next keynote, I will pass to Dr. Reyes and Dr. Montian at the chair for the next section, please.
Okay, thank you, Dr. Thammarat.
I'm
going to present the. Yes, sorry, Spider-Man. For the next two presentations, I'm going to introduce the presenters. The next keynote is going to be presented by Professor Penung Warnichai. He's going to show us some work on the recent research studies at IIT in earthquake engineering, vibration control, and structural health monitoring. Professor Penung comes from the Asian Institute of Technology. He received his doctoral degree in civil engineering from the University of Tokyo in 1990. He's currently a professor of structural engineering at the Asian Institute of Technology. He has been actively involved in research and practice in the areas of structural dynamics, earthquake engineering, wind effects on the structures, bridge engineering, and disaster management. Since 2002 until now, he's been the leader of a long-term research program on mitigation of earthquake risk in Thailand, funded by the Thailand Research Fund. He has also participated in many research projects from different universities, 3 government departments in Thailand. In terms of professional activities, he's been working as the chair of the chapter on the effects of earthquakes and wind loads at the Engineering Institute of Thailand from 2002 to 2016. He was leading a team of experts, professional engineers, to develop the first board member of earthquake.
Hello. I cannot hear you, Professor Garcia, but I assume that you already finished your part. Thank you very much for your kind the introduction. All of you can hear me well?
Yes.
Yes.
Good.
Yes.
Yeah, good afternoon and good morning to everyone.
But yeah, yes,
Let
thank
me
you.
start by sharing the screen. But it seems that I cannot share the screen. Can the host allow me to share the screen? I still cannot share the screen.
Oh, yeah, I will ask the host now. The host, can you allow him to share the screen, please?
Okay, it looks like I'm able to do it. Okay. All right, all right.
Yeah, we can see it now.
Yeah, it's there. Okay, we can see it now.
Okay, okay. Well, this is the first slide. Can you all see the slide? Can you see the mouse?
Yes, we can
Okay,
see the slide, but
yes.
not the mouse.
Okay. Well, the topic I'm going to present today is quite different from what presented by Dr. Professor Jack Kim. And I think it's quite different from other topics presented in this conference. But I hope you'll be interested, and I try to make it simple and clear. It's about the research studies at AIT by our graduate students in the area of earthquake engineering, vibration control, and structural health monitoring. Okay, let me start by showing this structure. It's a tall steel stack located in Rayong, about 200 kilometers from Bangkok. This is just an example of a vertical cantilever structure, which is quite flexible in lateral, and is quite vulnerable to dynamic wind effects. the structure can be easily shaken by the dynamic wind force. Now let me give you some rough idea. If you look from the top and see the cross section of the stack, and you see the wind is coming from the left, the wind flow, when it passes through the stack, it will create vortex flow. It's a rotational flow. The vortex that created will be in a periodic form. So it will create a kind of cyclic change of pressure around the stack. This cyclic change of pressure will produce a shaking force in a certain frequency. When this shaking force match with the natural frequency of the stack, it will create resonance. So it can produce a very large resonant vibration of the stack. The vibration may lead to the damage, the bending stress, high bending stress at the base of the stack. So there are many approaches that people are trying to solve this problem. This is one of the common approach, is to wrap the top part by helical track. This is to destroy the vortex formation on the top part. This seems to be a very popular approach, but I'm not sure about the effectiveness because some reports say that they are not effective. Some reports say that it's work well, but no matter whether it's work well or not, people are applying this one to the real world. This is another approach when you have a tall and slender stack. This is a structural engineering approach. You may want to try to stiffen the system by applying the stiffening truss around this. But the approach I'm going to highlight is this one, the structure dynamic approach, by installing this kind of blue color steel ring pendulum on the top of the stack. Okay. From the distance, you cannot see this pendulum, but if you take a close look, you will see the blue color ring hanging from the top of the stack. This shows you some idea how we hang the ring. Okay, the ring is hung by this steel rope at 3 locations. So it's kind of forming the pendulum that can swing in any direction. And at the bottom of the ring, we attach viscous damper. Okay, this forms the kind of system called tune mass damper. To make it work, we have to tune the pendulum frequency to match with the natural frequency of the structure. So whenever structure is vibrating, energy will be flow into the pendulum. Vibration energy in the pendulum will be dissipated by the viscous damper. This is a mechanism to increase the energy dissipation of the whole system. Okay, so this is a way we can actually solve the problem for the stack. But this idea is not just limited to steel stack. It can be applied to tall buildings. If you have ever visited Taipei, I think you may see this building called Taipei 101. And if you visit this building, I think you must have seen this one, a large pendulum on the top. We call the pendulum tune mass damper. It's a really large scale pendulum, and it's worked in a similar way to the pendulum tune mass damper I just explained. Okay, but the size of this pendulum is very large. We have a metal ball of about 700 to 800 tons in mass, hanging by the pendulum rope, the pendulum wire, with the pendulum arm is about 11 meters. So this is to just improve the energy dissipation capacity of the Taipei 101. Now, when you look at the structure of this pendulum, you can see that although pendulum looks simple, but the structure to hang this pendulum and to support this pendulum is quite complicated. And the pendulum also occupies quite a big space in the top part of the building. At AIT, we are thinking of a different system. We think that we can design tune mass damper in a different form. Okay, so we can put just the mass on top of rubber bearing, and this rubber bearing is kind of steel laminated rubber bearing, which is very stiff in vertical, but is quite flexible in lateral. So it can carry a lot of load, but it's quite soft in lateral. We found that it is possible to design this system to work like a Joule mass damper for tall buildings. You can design a system like 1,000 ton mass with a long natural period to match with the natural frequency of the structure. It will occupy less space. The construction is quite simple. Maintenance requirement will be low and the cost is low. I think this will be quite attractive to apply as the real dynamic damper for tall buildings. So if you come back to Taipei 101 and we want to, if you modify the design of Joule mass damper into the type we are interested, it will occupy only this small space. And you have the remaining space that you can use for other purpose. That is a very expensive space, you know. So if we can redesign the Joule mass damper into the new form, then we can save a lot of space, and it will be quite practical to put this kind of damper into many tall buildings. So this shows you the idea. We conduct a checking table test, create a model of this type of Joule mass damper. But this is a small size. It's about 2 tons mass. And we use a check table to simulate the lateral movement of the floor. And we put a vibration sensor to the floor and to the mass. So this kind of experiment is carried out by one master student, Mr. Pruk, just to be able to check its performance and make the correct mathematical model of this Joule mass damper. We found that it can be represented by a single degree of freedom system with some kind of softening stiffness behavior. Now, after Mr. Pruk, we have another student that followed this work, Mr. Chanon. Then he worked on the design of full-scale Joule mass damper. Okay, and then he studied what will happen if we put this one onto the 200-meter tall buildings. All his study is a kind of numerical analysis using finite element model and mathematical model, but use a model that developed by Mr. Pruk. So you can see that the idea is to put about 1,000 ton Joule mass damper on the top, tuned to the frequency of about 0.2 Hertz of the building. Without Joule mass damper, the lateral response on the top presented by horizontal acceleration is quite high, presented by the gray color. But after we install the Joule mass damper, the response reduced to the black color. So you can see the effectiveness of the vibration control system. Here is another way to present the result. We plot the x-axis acceleration on the top floor together with y-axis acceleration on the top floor. The gray color is the acceleration level without Joule mass damper, and the green one shows the one with Joule mass damper. So this is a quite effective device to control, but everything is still in a computer. We are actually hoping that we can apply this one to real buildings soon. At the moment, we are designing this size of Joule mass damper for one tall building in Pakistan. When the project is complete, I will come back and tell you again, maybe next year. Now I change the subject to earthquake problem, earthquake engineering issue. This is one of the school building in Chiang Rai, the northern part of Thailand. And because Thailand, we normally do not pay much attention to earthquake risk. Buildings that we built now have some problem. like this school. This school building have a soft story issue. I mean, the lowest story is weak compared to the upper story. And it has torsional irregular problem because it has a very large kind of masonry wall on one side, but no wall on the other side. This is for the staircase. So under the earthquakes, we found that columns in the first story actually suffer more damage. Columns in upper story almost have no damage. And of course, the damage increased with the distance from the staircase, which serve as a rotation center of the building. So this shows you some damage to the columns. We have so many school buildings that looks like this in the northern of Thailand, in the high seismic hazard area. So this shows you one project that we are trying to mitigate the risk by make a what we call seismic retrofit of a soft story RC school building by using buckling restraint brace. Okay, the brace is shown here by the black color steel brace. We put only a few brace into this soft story. This is a collaboration work of AIT, Nanyang Technological University of Singapore, King Mongkut University of Technology of Thonburi, and Chiang Mai University. So we work together and we actually retrofit about 4 buildings in Chiang Mai, Chiang Rai, and Chiang Mai. This is how it looks. The brace is not just simple steel brace. It will not be buckled under high compression. Okay. Well, under cyclic load, it will just yield in both tension and compression. And because it can yield in compression well, it can form a very good hysteretic behavior, very fat hysteretic loop. It can absorb a lot of vibration energy. Okay, this actually, the design of this one is the work of one master student, Mr. Hassan Tariq, in 2016. And actually the brace is a homemade. We actually designed and built it in our structural engineering lab at AIT. And we test the full scale specimen before we put it into the real building. Okay, this is when we pull it and we push, pull, push, this is under cyclic load. Okay, up to story drift of 3%. That means we confirm that the brace can yield plastically deform both in tension and compression without buckling. Now this is another view of the buckling restraint brace. It seems that we don't have to put many of them, just a few of them is good enough. This is confirmed by extensive nonlinear numerical calculation. And but if you go to Japan, you will find that this retrofit technique is very common in Japan, but it's not so common in many countries in Asia. In earthquake, high earthquake hazard countries like Philippines, Indonesia, or Myanmar, I think we need to apply more of this kind of technique. We need to promote the use of seismic retrofit technique. Now I come to another topic. You may know about this concept, base isolation. Instead of modifying a structure, we can modify the base of the structure. Instead of connecting them to the ground, we put base isolation bearing underneath the building. Again, this bearing looks like the same bearing we use to construct TMD. It's a kind of a rubber bearing with steel plate inside, we call steel laminated rubber bearing. This type of bearing is very stiff in vertical, and it can carry a lot of vertical load, and it's very soft in lateral. So when we put it underneath the structure, the performance under earthquake will be much better. In Thailand, the Department of Public Work is thinking of applying it to this technique to some important government building in northern of Thailand. and I was involved in this project. So I brought this problem and to AIT and give it to one master student, Miss Acharapan. Okay, I asked her to design the best isolation system for this government building. So this shows you how she made it. So she designed the base isolation system by using commercially available base isolation bearing. Okay, we did not design a new bearing system. We just use whatever available for commercially. And she actually select about 5 different type of bearing, put it underneath each and every columns of the building. And then we check how it will work. But to understand this, I think we need to see the performance of the structure without base isolation first. This is called fixed base building under design basis earthquake. So we calculate the response by using a computer program called Perform 3D that can simulate the response, calculate the cracking damage. Well, but the deformation of the structure is exaggerated by the factor of 70. We amplify it 70 times so that you can see the movement. Okay, in reality, it will not deform this much. And the color code show the level of damage. If it's yellow or green or blue, the damage will be small. But if it's red, the damage is near its capacity or already exceed the capacity. So it means that this structure, after subject to design basis earthquake, you will have extensive damage inside the building. Now this is the same building, but now we put on base isolation bearing. Okay, the performance will be quite different. This time, the structure is still deformed. It still has some damage. But from the color, you can see that it is not so strong. And there's a lot of movement at this level, in a base isolation layer. So the structure will be protected. There will be less damage to the buildings. In fact, there will be less impact to the content and to the people inside the building as well. So this is the effectiveness of base isolation system confirmed by our study. Now, if you go to Japan, you find that they actually apply base isolation not only to small buildings, not only moderate sized building, but also apply to tall buildings. That is quite interesting because it's quite amazing to see that this tall and slender, and you still can put isolation bearing underneath the building. Here, when we visit Tokyo Institute of Technology, Professor Kazuhiko Kasai, he brought our team to see underneath the building, a tall building in his campus, and he showed the base isolation system applied there. But what I want to highlight is in Japan, you may know or you may not know, but the structure of tall buildings are steel frame, okay, or sometimes brace frame like this one, but not the frame with shear wall. In other countries in Asia, we use frame with shear wall. So our basic structural system are quite different between structure of tall buildings and structure for tall buildings in Japan. So I'm quite interested in this one. So I asked 2 master students to work on this one. But before understanding this one, maybe I have to explain the basic dynamics of these tall buildings under earthquake. Now, the tall building have many vibration modes that will be excited by the earthquake. This is a response of the first mode. The structure will be simple sway to the left, to the right. It will create a shear force that vary along the height and overturning moment. Everything will be in linear proportion, and they will be proportional to what we call modal coordinate of the first mode. The structure will vibrate at long period. This is a second mode in tall buildings. Okay, and again, the pattern of deformation is different. The pattern of shear and overturning moment are also different. But all these response will be proportional to the modal coordinate of second mode. And this is a third mode. The structure itself have many vibration modes. When it's under subject to earthquake, all of these modes will be excited. And what we will see is a combination of all these modes. So you can see the displacement. It's not just simple sway in the first mode, but it's combined with the second mode, third mode. The shear force will be in very irregular pattern, same as overturning moment. But you can draw this kind of dotted line, mean the upper bound on the left, upper bound on the right. This is called seismic demand or shear demand. This is also show the overturning moment demand, which is means the maximum response produced by the earthquake, okay, over the entire time history of the response. Now come back to the base isolation. So again, I actually asked a student to work on this one. One of that is Miss Anastasia from Indonesia. Again, this student is interested in this issue because she's coming from an earthquake country. Another one is Miss Nimala from Nepal. Nepal is also has been subject to earthquake recently. So this shows the result, which is quite interesting. This shows the storage shear, I mean the maximum shear load, fixed base and isolated base, the red and the green. When you put the isolation bearing, then the response reduced to the green, from red down to the green. So you can see a big change in the storage shear. And here is storage drift, which is an important response parameter. You can tell how much cracking it will happen to your partition walls or the damage to the frame by this storage drift ratio. Again, you can see the big reduction. Peak floor acceleration is associated with the impact to the content and furniture inside the building. So the big reduction again. So I think this is a very effective measure confirmed by the study. So we are now working on some project in Philippines on this kind of base isolation bearing system for tall buildings. Let's see. Now I come to the last topic I want to highlight. It's about seismic health, structural health monitoring system. Okay, you may know that in many tall buildings, we put some vibration measurement sensor inside the building. And this is the most common type of the sensor we use. It's called accelerometer. Because this type of sensor is very simple, very compact, and low cost. So we can put some of them at some floor. Okay. The idea is, how can we make use of this data to rapidly identify the impact of earthquake to the building? When the building is subject to earthquake, the structure will vibrate. We will have this record of acceleration. How can we use them to actually calculate and check the safety of the building? There's a traditional way to do this. One is to use this sensor signal to estimate the natural frequency, mode shape, damping of the system. It's called dynamic properties before and after the earthquake. If there's a big change in the natural frequency, damping, or mode shape, you may be able to tell that there is some damage. But we found that this is not a really effective approach, because even the structure have serious damage, the change in frequency or mode shape will be quite small. Our approach is different. Our approach is presented by this idea. Instead of trying to find this dynamic property, we are actually, from the acceleration record, we are trying to extract modal coordinate. And from the modal coordinate that we obtain for each mode, we can compute the response of various kinds: inter-story drift, flow acceleration, story shear, story moment. And then we can sum the response of all the modes that participate in this. So I do not have time to go through it.
Professor?
Yes.
Yeah, I was about to say we only have 3 minutes left, please. If we can wrap it up.
I'm about
Thank you.
Thank you.
Okay, excellent. Thank you.
So this is the idea. We can actually predict from acceleration record. We can compute the shear. We can compute the moment, and we found that it can be quite accurate. But I want to jump over this part because we don't have much time. What I want to show is not only we perform numerical analysis, but we also conduct some experiment. Okay, this is a simple 8 degree of freedom. That's just a vertical beam with mass lump at the some floor, and we put accelerometer. We also measure bending strain and shear strain inside this building, inside this structure at some location. The idea is to test the concept. The idea is we will use acceleration record to estimate the shear and bending moment at this location and compare whether we can actually estimate this accurately or not. So we measure our acceleration and shear strain and bending strain, and we check the idea. So this is show you the test. Sometimes we check at a low amplitude and sometimes at large amplitude. So this one will give you an idea. Okay, the green one is a floor acceleration, but the top picture shows the bending strain at some location, and the red one is the bending strain estimate from acceleration data. The green one is direct measure bending strain. So I think you can see that we can predict the strain quite accurately. And that is not just one location, but also we can predict bending strain at the base, shear strain at the base, bending strain at the mid height, shear strain at the mid height. It means that from one type of response, we can calculate the response of various kinds at various components in the building. And we can actually use that to compare with the acceptable limit to all these components inside the building. We are in a plan to actually apply it to real structure soon. So when this is done, I will come back again and tell you our new story. Okay, I think that's all for my presentation. Thank you for your attention.
Thank you very much, Professor Penung. A very interesting and educational presentation too. We have time probably for a very quick question. If there is anything burning, please shout.
Okay, there's a one.
Okay, everyone is keeping quiet. Yeah, that's okay. If you have any questions, I'm sure Professor Penung will be happy to answer on the chat, or you can email him directly. Thank you again, Professor.
Thank you. Could I ask some
there is a question? Yes.
Yes,
yes,
okay, my name is Panuma Sangam. Could I ask Professor Penning about just a couple questions? The first question is about the first study about the June mass damper. Professor show about the result of the acceleration on the top. Could I ask about the displacement result? Is this much better? For the acceleration is decreased about half of the normal before before TMD, and after TMD the acceleration reduced about half. How about the displacement? Could I ask Professor about displacement result?
More or less the same.
More or less the same. Okay, yes. It means like the displacement decreased about half, about 50%. Okay, yes. Thank you, Professor.
Yeah, because it's controlled by just a few modes or a single mode. So the response, acceleration or displacement are more or less in the same proportion.
Okay, yes, it means like the displacement and acceleration reduced by the effect of damping instead of like the effect of the stiffness, right?
By the additional damping, yes.
Okay, yes, thank you very much, Professor. For could I ask about the next question about the retrofit by the BRB? First of all, I would like to thank you, Professor, to introduce like this device to the seismic retrofit of the Thai building, which I'm also interested and I'm studying on this study also. Could I ask about like Professor said like there are 4 buildings which retrofit BRB in the North province, such as like Chiang Rai and Chiang Mai province. Could I ask?
Only one building.
Only one building and how?
Yes. The other we use column jacketing because that's easier by our local contractor to do that.
Okay, I understand. Isn't it like
have to do it from our lab?
Okay, thank you, Professor. I understand. Okay, yes, thank you very much, Professor. This is my honor to ask Professor a question.
All right.
Okay, thank you.
Okay, thank you very much to both. Let's move on quickly to the next presentation, please. The next presentation is entitled Practical Use of CFRP for Strengthening of Reinforced Concrete Structures, and it's going to be delivered by Professor Amon Pimanmas from Kasetsart University in Thailand. Professor Pimanmas is a full professor at Kasetsart University, Thailand. His research interests fall within the area of composite structures, reinforced concrete, and seismic behavior. He's currently the president of the TSEA Structural Engineering Association. He's also a member of the board of directors, Mass Rapid Authority of Thailand, and the Aeronautical Radio of Thailand. And as a personal note, I have to say that if you are doing work on bond slip or wrapping of columns with bond slip and slab splices, you definitely need to read his papers, because I had to do it for my PhD. So, Professor Pimanmas.
Yes, me too.
Yeah. I think you're muted, Professor.
Yeah.
Okay. Thank you very much. Can I start?
Yeah. The floor is yours. Yes, absolutely. Thank you.
Okay. Thank you very much for inviting me to join this symposium. I'm very happy to present some of my work. Actually, this is not what I'm going to present to you is not my it's not my research. It is because the topic that I have been assigned is the practical use of CFRP, carbon fiber reinforced polymer, for strengthening RC structures, a case study. That's why I try to find out one of my past design projects that I have been involved as a main designer, and to present to you. So if you expect a research project, so I'm sorry. Actually, I have some research about FRP, but today my topic would be the practical use. Okay, because I think it will be useful for Thai engineers. Okay, to learn or to have some experiences regarding the actual design and implementation of carbon fiber reinforced polymer in Thailand. Actually, this is 10 years back. One day I have got a call and they want to contact me regarding cracks that are found in the 7-story car park structure in Bangkok. Okay, so they send me some picture of the cracks. And this crack have been found near column. Okay, almost all columns starting from the 2nd to 7th floors. Okay, so then I have been invited to the structure, to the building. It is car park building, and I want to observe what really happened there. Okay, so I have found that most of the cracks are radial cracks. Okay, it emanates, the cracks emanate from the column location toward the slab. And I have found that the crack appears on the top face of the slab only. There are no crack at the bottom face. Okay, as far as I can see from my bare eyes. And I have also checked whether there are a crack on the top face or not. So the cracks are looking like this. So at first I think there may be some problem regarding the moment strength, because as you know, if you study RC structure and if you study a flat slab and flat base structure, you can see that there will be two kinds of crack at the column location. The radial cracks like this. Okay, these are the cracks that may be resulted from the bending strength, and also another crack like this. This may be cracks due to the shear and punching shear at the column location. Fortunately, there are only radial cracks. They are not. I have not found any peripheral crack around the column. Okay. So the step, because I have been invited as the designer, as the investigator of this problem, and to help them solve the problem of these cracks. So we perform the background study why this crack has happened, the cause of cracking, and then we want to check based upon the information that we have, the evaluation of the existing strength. We have done finite element modeling of this structure, analyzed for internal forces, including moment and shear. We have decided to remedy the deficient punching shear strength as well as the moment capacity at the negative moment section. And then we also recommend load test to verify our design. Okay, and also if the load test pass, I can get the design free. If the load test is not passed, so I may have the problem. Okay, as a designer. We have referred to the ACI 31805 building design code at that time. Okay, because 10 years ago, and then we also refer to the ACI 440 guide for FRP design and construction, and then ACI 437 strength evaluation of existing RC structure to undertake this project. Okay, so as I mentioned, the cracks are found in a negative moment zone. So my first thinking is that it might indicate the insufficient bending strength in both directions. Okay, but this can be confirmed through the finite element modeling and to the existing drawing that show the existing amount of the negative reinforcing bar. Okay, so but before that, we also want to investigate the cause of the cracks, why this crack happened. We check the material quality and the workmanship. This structure is 30 years ago. Okay, it means that it has been constructed more than 30 years already. And I have found that the concrete surface condition is quite bad. And you can see in many locations, the aggregates, sand, gravel are detached of the surfaces, despite the car with low speed, because it serves just the, not the truck parking, car parking. Actually, this car park is in the university, one of the private university in Thailand. Okay, so the car with low speed. So, but you can see that the surface is quite bad like this. So I suspect that the concrete quality is poor. And also not only that, but also the construction is also poor in terms of the concrete pouring, compaction, vibration during construction. But we don't want to talk much about that, because otherwise it will indicate and it will point out to many persons involved that might not be good. So that's why I try to keep as my internal information in order to know what really happened. Okay. So then after I have been assigned to be the principal designer, I ordered a short blasting of the entire floor to identify and to review, to see the crack more evidently. And we have found that the crack has a pattern. Okay, then especially around all the columns in all the floors. Most of them have width larger than between 0.5 to 1.0 millimeter. And despite the ACI allow only 0.3 to 0.4 millimeter. So this means that the cracks are already exceeded in terms of the allowable width, okay, based upon the acceptable design code. So this one have been, so I think this is the structural crack quite clear, and we have to do something to strengthen, okay. But the owners say that they don't want to increase the live load. They are happy at 400 kilogram per square meter live load as for the requirement of the law according to the car park structure. But they want to confirm that the structure can be remaining in service. Okay, so in that case, I think the problem is become easier because the live load requirement is not increased. So we just want to remain the capacity. Okay, so this is the this picture also show you the crack location, radial cracks. So this is the crack mapping, and you can see all floors, second to 7th floor happen like this. Okay, but still no signs of punching shear crack. Okay, except the radial cracks, and this show you floor this one is for 6th floor, and this one is for 7th floor, the same pattern. Okay. Not only concrete quality, we also check the reinforcement condition, because we have found that the concrete cover is quite thin, not meeting code requirement. Okay, most of the location, the cover concrete is only 10 millimeter or less than 10 millimeter. And we have seen that some steel bar show sign of lasting already. Okay, with some have already exert the pressure outside and to the concrete outside and to break out, and still area is seen to be reduced. And this might bring about another cause of the lower bending strength. Okay. Now we start to analyze the structure by using finite element modeling. Okay, so this one we have plot the moment diagram along X direction for both middle and column slip with today commercial software. We can easily find the moment in any location in the slab. Okay, and then we can check against the existing reinforcing bar. Actually, because the building is 30 years old, so no drawings, but because the building is flat slab, RC flat slab, so we suspect that the reinforcement should be have a same pattern for all column location. That's why, based upon the earlier investigation, we have found, based upon the coring inside the structure and to see and thorough scan of reinforcing bar, we have some some drawing to show the existing amount of reinforcing bar. Then we can check, we can compare, okay, against the moment. So, and this is shear diagram. The major problem that I have found for this structure is the punching shear, because everybody knows that the punching shear is brittle shear failure mode. And in terms of the bending strength, even though the crack are radial crack and showing sign of the insufficient bending strength, but maybe they can have some mobility distribution. Some plastic hinge may form, but punching shear, it is quite brittle. That's why I'm quite concerned about the punching shear failure mode. So we check the punching shear ratio, and we have found that in many locations, okay, the punching shear ratio is exceeding 1. For example, you can see this one, 1.114, 1.112, exceeding by 10%, or some location by 20%, indicating the major problem that we need to urgently strengthen this structure. Okay, so our target is to make this ratio less than 1. Okay, to avoid punching shear failure problem. Of course, there are many ways that we can do this. Okay, some designer, because in this project, it is quite big project. There are many designers involved. There are many engineers involved. Some designer present, casting the drop panel, underneath the existing slab. But I don't recommend that choice. I will tell you later why I don't recommend that choice. I recommend the steel bracket. Okay, the steel bracket will be installed on the column faces to increase the perimeter of the column and to enhance the shear strength. Okay, so this means that the steel bracket shall be designed so that the punching shear ratio should be less than 1. Okay, and so finally we have designed several types of the steel bracket. Some column need steel bracket on 4 column faces. Some need only 2 opposite faces. So there are various types of the steel bracket condition here. We have found the problem once we finish the design of steel bracket and we want to install this steel bracket on the column face. We have found big problem. We cannot do that because we don't know the actual condition of the inside reinforcement in the column. You can see the location of the bolt. Okay, it coincides with the existing reinforcement bar in the column, so that we cannot install the steel bracket. We have to redesign, and then we have found out that this problem we need to be more careful, especially it's not the new construction, it's the installation of the bolts to fix the plate of the steel bracket into the column face. So the furrow scan need to be done for all column faces and for all column. And the design of the location of the bolt shall be customized for each face of each column of each floor. Okay, so and the detection of the column rebar location can be done easily by furrow scan technology. So the design has been devised to in order to successfully drill the hole and to put the ball into the column. So we have used this kind of the steel bracket instead. Okay, and there will be type A. Type A, we fit the steel bracket on the narrow side of the column face. This is the steel bracket on the opposite side of narrow face, and also type C, we put on the wide face of the column face. Okay, depend on our design whether we will apply type A or type C steel bracket. And most of the column do not require steel bracket on column on 4 faces. Okay, most of them require just 2 opposite faces. We have to just select whether to put it on the narrow or the wider face. And of course, there are still many other obstacles. There are many pipes. Some pipes can be removed, but some pipes the owner said you cannot remove because it is the pipe that maybe they have some wiring for their security or some other things. So we need to redesign again and again. That's why until we can get the customized steel bracket for each column face, for each column, for each floor. Okay, and then the way that, and for some column face, after we have done furrow scan, we are very surprised of the original construction. You see why they construct like this. This is what the furrow scan have reviewed, have shown to us. The steel bar, no spacing between steel bar at all. No place that we can install the poles. Okay, so but anyway, we can find out the solution finally. Okay, and then we have to fix the ball first. We have to fix the ball first, and then we have to put the cardboard to the drill location, and then we send the cardboard to the steel fabricator to fabricate the steel plate according to the location of the hole. That's why it shall be customized for each column face. Actually, the use of steel bracket has been successfully done beforehand. Before this project, if you have traveled to Siam Paragon, you go to the underground car park, you will see also the installation of steel bracket to resist the punching shear capacity. That is also my design. Okay, I have been used the steel bracket before for this department store. I think of just 3 or 4 years before the car park structure project has been my supervision. Okay, and now just the figure show you how they install the epoxy anchor bolt. They fix the epoxy. They fix the bolt with the epoxy to install the steel bracket, and the gap between the bottom slab and steel bracket is filled with epoxy injection or with cementitious grout. For Siam Paragon case, it has filled with cementitious grout, but for the current car park structure case, it has been filled with the epoxy grouted. Okay, this just show you, and this one is the car park structure case. Okay, and then we also recommend load testing of this structure by using the sandbag. After you can see, this is the result of after they install the steel bracket like this. And then now the punching shear ratio is any location less than 1. And this is the load test. Okay, the load test. The test result show that the deflection, the measured deflection is 3.09 millimeter. Comparing against the ACI code, the allowable deflection is 6.91 millimeter. So this project passed the ACI, load test criteria. Okay. So as I have mentioned before, DAY2 engineer, they proposed the drop panel option. Okay, against steel bracket option. So actually the initial design is that in order to solve the punching shear problem, they will install the drop panel, the concrete cast beside 2 drop panel underside the existing slab. But I recommend them that I will not adopt this choice because I think there might be a separation between the existing slab and the drop panel and making it difficult to create the composite action. Okay, and moreover, drop panel may also increase the loading to the slab. Okay, because drop panel, the proposed drop panel is 15 centimeter thick. So I say that a separation may occur due to you have old concrete. You want to attach new concrete to old concrete, and because they will have different shrinkage performance. That's why they will not shrink at the same rate. So it might be likely that a separation may occur. And if a separation may occur, the weight of the drop panel will accelerate the punching shear failure. That's why it should not be adopted in this project. I say that we should adopt steel bracket because there have been reference projects, the Paragon project, and the drop pan and the steel bracket is supported to the column directly, not creating load burden to existing slab. Okay. Now the other thing is the carbon fiber, because now we have solved the problem of the punching shear already by using steel bracket. So the remaining thing is to remedy the deficient bending strength through the carbon fiber option. And we have surveyed the market at that time. There are actually, as you know, there are 3 major types of fiber, right? Synthetic fiber, there's carbon, aramid, and glass. But aramid is not so popular. So at that time, there are carbon and glass fibers. Both of them have been used, but not in many projects in Thailand still at that time. I remember because the carbon fiber come to Thailand, I think not more than 20 or 30 years back. At that time, not many people are feeling good to use carbon fiber. But nowadays, it has been used quite a lot already. So the owner asked whether we should use carbon or glass. The cost is quite make a difference between using carbon and glass fiber. Okay, so everybody know carbon fiber is high in terms of the cost, and glass fiber is quite low. And in terms of performance, strength, and modulus, also carbon fiber has higher strength and modulus than glass fiber. So of course, I defend carbon fiber because I say that the carbon is inert substance. It's not easily reacted with environments. It is also quite durable. The glass may have problem, may easily reacted with concrete because concrete has alkali property. A chemical reaction called alkali silica reaction may occur, and it may degrade the concrete quality. Because now your concrete is not good already. Even though there is the alkali resistance glass, but we still are not quite sure about their performance in the long term. That's why for exterior application like car park, it is recommended to use carbon fiber. And then we have to decide what forms of carbon fiber to be used between sheet and laminate. Okay, actually ACI code allow both forms. The sheet is 0.11 to 0.22 millimeter thick. The tensile strength is about 3,500 megapascal. And as for the FRP laminate, it is 1 to 2 millimeter thick with tensile strength of about 2,400 megapascal. So I recommend them to use the FRP sheet because we install at the top of the slab. Okay, if it is installed at the bottom, maybe we have to think another option. But in case of the top slab installation, so maybe it might be better to apply sheet because sheet is thinner than laminate. If it is thinner, it means that in order to get the same strength, you need more contact area. And if you have more contact area, you have wider width, so it may be more difficult to peel off from the surface in terms of the bonding, because this is the external application of carbon fiber material. And finally, the owner accept the choice of sheet in this project. Okay, there are many reference projects that use sheets before in terms of the avoiding the delamination. And also I have found the ACI code formula. Okay, so the ACI code allow higher ultimate strain and strength in the sheet. This is called the debonding strain. The strain at which the sheet is expected to debond, or the FRP is expected to debond off the surface. And it is directly, it is inversely proportional to the thickness of the fiber. So if you have larger thickness, so this strain will be lower, meaning that it is easier to detach. That's why the thinner might be better to make the debonding strain become larger, and so that we can use it more efficiently in terms of the strength property. So we have adopted the design and the design formula according to the ACI 440 guide to this project. Okay, so the framework of the ACI 440.2 ROS. Okay, the name is the Guide for Design and Construction of Externally Bonded FRP System for Strengthening Concrete Structure. So the first criteria is the ultimate strength. Okay, the resistance shall be less than the design strength. And then we have also checked at ultimate level, ultimate limit state, and serviceable limit state. Because not only strength check, we also need to check at the SLS as well. That is to prevent excessive diffraction. Stress in rebar shall be limited to be not more than 0.8 Fy. Stress in existing rebar. Even though you have installed carbon fiber and you use carbon fiber to resist the load, but you have to make sure that the stress in the existing rebar shall not be too large, and it is limited to 0.8 Fy to avoid excessive diffraction, and also to prevent the degradation due to creep and fatigue, especially in the car park project. FRP, the stress in FRP is also limited to this value, which is 0.55 FFU for, there are many values. I don't remember all of them, but we have checked against this criteria as well. And we have developed the design worksheet, okay, for this one with input material properties. One thing is that we have to take into account the existing strain due to dead load, because you have to understand that in this case the section is not starting from the same strain point. Some concrete, okay, at the bottom face, at the top face, also some inside steel, existing steel, they have already some strain already, but the carbon fiber starting from zero. Therefore, in this case, we have to account for this incompatibility in the strain in order to calculate, okay, the performance.
Professor,
okay, so finally we come out.
We have 3 minutes left, please.
Okay, yes, I'm almost finished.
Thank you.
Thank you very much. So this is we come out with the drawing that show the carbon fiber placement, okay, along X direction, along Y direction. Of course, most of them are top carbon fiber at the top, and we have overlay the crack pattern and to see the location of the fiber together with the crack pattern. Okay, this is 7th floor, and actually we have some video, but this is the PDF, so the video cannot be run. This is the installation of carbon fiber in along X and Y direction according to the design. Okay. This one we have found out some what we call air pocket like this due to maybe the contractor, the installer, the people who install this carbon fiber, they the project is quite big, so that's why there may be some locations. So I also need to decide to strengthen or to at some local point in which they need more carbon fiber to solve this problem. Okay, some air pocket inside. And this one show you the Siam Paragon project. Siam Paragon project also almost the same pattern, that is we have steel bracket for punching shear strength, strengthening, and also for the we also use carbon fiber. But for Siam Paragon project, we use another method. We don't use sheet in both directions. We use the what we call near surface mounted. So we make the groove into the concrete face in just the cover, and then we put the fiber in this direction, and then another direction we also put the cover in this direction. Okay, so this is the Siam Paragon project. So grooving and okay, so yes. Siam Paragon project, I remember at that time they want to increase the live load from 400 to 800 kilogram per square meter, because they have Kume market and they want to, they said that the truck, the car that carry the stock, the products is quite heavy load compared with the initial design. So they want to increase the live load from 400 to 800 kilogram per square meter. And this is the load test of Siam Paragon project. We install the LVDT to measure the diffraction at 2 locations. Okay, this is the gate, the dial gate they put in the 5 gate per each panel have been installed at the bottom face to check the deflection, and all of them, of course, have passed the load test criteria. So, and they have compared well with the finite element calculated deflection among the analysis and the measure value. Okay, so I think at this moment, these two projects are still in good service. 10 years, more than 10 times Paragon, more than 15 years ago, still no problem. And the 7-story car park structure also more than 10 years ago, still no problem. So I think this can be the two projects that can be, good experiences, good present for designer in Thailand, how they can apply and adopt the carbon fiber to strengthen their structures. Okay, thank you very much for your attention. I think I not overspend the time. Okay.
Thank you very much, Professor Amon. I think there are a couple of questions in the chat. I would be grateful if you can answer them later on at your convenience, please. Unless there is a burning question, a very quick one, because you were already late.
I can, yeah, so maybe because maybe I can contact later, because in fact I was a little bit confused about this strategy, because, well, first of all, Professor started presenting or demonstrating that it's necessary to increase the punching capacity. But later, in fact, it applied the CFRP for the flexural. So in the beginning, we saw flexural cracks, then it was punching, and finally applied a flexural strength strategy. And it is, in fact, a little bit confusing for me, mainly because they at the same time indicate that the quality of the concrete is very low, and consequently, we have a high probability to have a premature debonding. Furthermore, it is also necessary to take into consideration this is a hyperstatic system. So what happens is that when we have an hyperstatic system, and when we increase only in the edging region on the close to the columns, so we have in reality we are increasing the load carrying capacity of the slab is very small, because we have the high probability to form an hinge in the positive bending moments region. This is very evident in tests when we test the continuous slabs or continuous beams, and this is demonstrated in several papers. So at the end, to be honest, I stay a little bit confused about the final configuration. So my question is, well, do you believe that this flexural reinforcement is the most efficient? Because for this case, for instance, I have already several times installed the NSEM system, because it's much more convenient because we don't see nothing in the top. So because laminates, as you know, are introducing concrete cover, and then we introduced embedded root section, introducing bars in holes in the around the column in order to solve the problem of punching. So this is normal design strategy to increase simultaneously the flexural capacity and the punching capacities, combining NSEM and also embedded root sections for solving these two problems. So to be honest, I say a little bit confused at the end. Can you describe what is at the end, what was the final purpose of this configuration, please?
Okay, thank you very much for your question. Actually, we have two strategies. The first strategy is we use steel bracket to strengthen the punching shear. We have not used carbon fiber to strengthen punching shear. Okay, so in the beginning of my presentation, I showed that the punching shear ratio is higher than 1, indicating that there is also a punching shear failure problem. And to solve that problem, we apply the steel bracket option to increase the punching shear strength. This is the example of the steel bracket that I have applied. to increase the punching shear capacity. But
Professor, the evidence are flexural cracks. So in order to, since the ratio between the design value and the design and the weighting shear force is no more than 10%. So, well, if you use a more complex models, like take in consideration the real nonlinear behavior of the materials, maybe you will not have this 10%, maybe it will be less than 1, because it seems that you use linear elastic analysis according to the figures that you present. So linear elastic analysis is a very, I should say, conservative approach when we make a design for strengthening. When we make a design for strength, it is fundamental to use a material nonlinear analysis in order to have a more accurate prediction of the real weighting forces that are in the elements. So this is why I'm a little bit afraid that the final decision is.
Because because I am afraid that the punching shear strength is, it is brittle variable and it has no redistribution. So in this case, if the one column has failed by punching shear, it may be progressive collapse may happen. That's why, and we also don't know the inside condition of the concrete strength. That's why
I think they only strengthen some of the columns, Joachim. I think they didn't strengthen the whole building. At least that was my understanding. I think we probably need to carry on the conversation for later, because we are running.
Yeah, we will be contact. I will contact Professor.
Definitely.
Thank you.
I leave it to you guys to decide.
Okay. Anyway, thank you very much.
Sorry, there's some questions from the chat box. Professor Amon can probably kindly just answer in the chat box.
Yes. Let me read first. There are 2 questions in the chat box.
But you can answer them.
Yeah, you can answer in the chat box later on.
Thank you very much.
Okay, thank you very much. Yes.
Okay. Thank over to you. Thank you.
Thank you. So we move to the next speaker. The next speaker is Associate Professor Mauricio Guadagnini. He is a senior lecturer in the Department of Civil and Structural Engineering of the University of Sheffield. He had more than 15 years of research and in the field of experimental mechanics and advanced modeling of concrete elements using both conventional and novel reinforcing systems. He had participated in several EU and nationally funded projects, and he is currently involved in the FP7 funded projects, Anagen NISI, which examine the innovative use of all-type components in concrete. And the title of his talk today is Natural Fiber Reinforced Mortars for Structural Applications. Welcome, Professor Guadagnini.
Many thanks. First of all, can you all hear me okay? Can you see my screen?
Yeah, we can see your screen.
Well, so thank you for the introduction. Good afternoon, everyone. And thank you also the chairs and the organizer of the conference for inviting me. It's a real pleasure to be here. And as the title says, my presentation will be about exploring the possibility of using natural fibers in structural applications. And I will be drawing from the experience that me and my team had here at Sheffield. So I will show also some of the research work that we're doing on this topic here at the University of Sheffield. And just to clarify, when I talk about natural fibers, I will only be talking in this presentation about natural fibers derived from plant and vegetable fibers. So the natural fibers, we can have fibers coming from animal or also mineral product that can be used to develop natural fibers. But I will be focusing mainly on plant and vegetables. So I will be talking about flax, jute, hemp, this type of fibers. And this is actually the fibers that we've also used in our research to explore the possibility of developing sustainable reinforcement. And plant, why we we started being attracted by the use of natural fibers is fairly simple, I guess, is because they are very sustainable and they are abundant. They grow everywhere in the world. This is just a map to show, to summarize the production of natural fibers in the world. And we see that quite a lot of actual natural fibers are produced in Asian countries. But everywhere in the world, you have different type of plants that you can draw on. And this is also very attractive because it makes it a resource that is available locally. And it can be used and exploited locally by making it a very affordable type of material. Natural fibers has been used for thousands of years. We've seen examples everywhere of fibers being included in mud bricks to make sure that we can develop some structural bricks able to resist shrinkage and give a plastic behavior, but they're also used in strawberry construction to build walls and housing. And they are renewable. So some of the plant species also grow fairly quickly, and you can have a crop or multiple crops a year. They are biodegradable, so they hit all the spot for all the check marks of being a very sustainable and low-cost material. And in terms of also production, when compared to more advanced synthetic fibers, they require much less energy. So all of these make them very desirable type of materials. In terms of cost, as we said, that they are cost effective. And if you compare it to more advanced materials like glass and carbon, there were a few talked about using this type of fibers for composite in previous presentations. This is how they fare, how the natural fibers fare in terms of cost per weight. So they are relatively cheap, but it's not just the cost that is attractive, but it's also their specific weight and stiffness. So if you compare them to glass fibers, it wouldn't be fair much to compare it to more advanced fibers like carbon. But if we compare them to glass, which is like a comparably cost-effective high-tech fiber, we can see that natural fibers have a relatively high strength-to-weight ratio, as well as a high stiffness-to-weight ratio. So in terms of giving you strength with the possibility of lowering also the overall weight of the structure or the reinforcement, this gives quite a good benefit, and it is attractive from a structural point of view. Now, the fact that we are dealing with natural products is not really a good advantage, in the sense that the chemical composition of the fibers that we're using is very variable. The three main constituents of natural fibers are cellulose, hemicellulose, and lignin, which kind of equate to, if you wanted to compare it to structural performances, is they make up the reinforcement, the matrix, and the bonding agent between your reinforcement and the matrix. But because of the natural nature of this type of fibers, the relative content of the constituent changes depending on what type of fiber you're looking at, where this geographically has been harvested, and also how this is being extracted and manufactured to make it a commercial product. Which means that when you have natural fibers, you are dealing with a material that is highly variable, both in geometry as well as in mechanical properties. So it's not, so this poses a challenge in when we want to use it as a structural material, because we need to really deal with a material with higher variability than material that we are used to. And also, natural fibers are thirsty. They absorb a lot of moisture. So this can be an issue when we want to use it, for instance, in application together with concrete or plaster, because they absorb moisture that they can expand and create micro crackings within the matrix, and then eventually lead to debonding between the fibers and the matrix surrounding it. Another issue that we have with natural fibers is that they don't really like much alkaline environments. So again, that poses another issues, especially if we're thinking of, again, including them in matrices like cementitious matrices or lime mortar matrices. Because eventually the alkalinity of the surrounding environment will create degradation of the fibers, and then we will lose the strengthening effect that the fibers can give to the surrounding mortar. But there are quite a lot of opportunities that has been seen by structural engineering, but first of all by composite manufacturers, and also given that we are able to develop textile that are fairly intricate in terms of their geometry and the weaving pattern. This can be exploited as in different types of applications. And one of the main companies, or one of the main uses of this nowadays is to be used as reinforcement for thermoplastic or thermosetting parts in the automotive business, but also in the sports business. And there is also the using of biocomposite, using natural fibers and bioresin, is also coming into structural application more and more. Here on the right, you can see a drawing or an artistic impression of a bridge that is planned to be built in the Netherlands, close to Amsterdam, which will use, or it's planned to be used, to be using a deck that is fully made with biocomposite materials, including natural flax fibers and bioresins. So again, we can see that there is quite a lot of interest from the construction industry. And when embedded in resin matrices, the natural fibers can be protected from the environment. So the durability issues that we've seen earlier on can be in a way mitigated. The things might not be as good in terms of durability when we look at structural application in concrete or cement-based matrices. But we see quite a lot of opportunities also in this type of applications, especially if it can be used natural fibers as short fibers, so in a way to replace the steel fibers or plastic fibers that we use now in FRC, going back, basically taking inspiration from the mud bricks that have been used for millennia. And they can be used to control shrinkage, or in application like fire spalling. So they can provide given properties to concrete. Or they can be used in textile formats, a similar way as we would use them in to produce bio FRPs. They can be used in immersing resin in the thermoplastic or thermostatic resin, or they can be used to develop natural fiber textile reinforced mortars, where the textile are embedded into a matrix that can be either cementitious or lime-based. The experience that I wanted to discuss today that we had here at Sheffield is mainly dealing with, well, we've done some work on short fibers as well, but I will focus this talk on the use of natural fiber textile reinforced mortars. So where we're using textiles embedded in mortar matrices. And this combines with the work that we do on strengthening for earthquake, or for seismic strengthening. And we've seen a lot of potential, or we've been kind of interested by using this technology, because most of the building that suffer from seismic deficiencies are unreinforced masonries. And most of these buildings are also located in developing countries, where again the cost effectiveness of the solution that is to be used is very important. Nowadays, we have quite a few different type of solutions for improving the seismic resistance of reinforced masonries. And a novel or the new emerging technology is that of textile reinforced mortars. But most of which is fairly consolidated now as a strengthening technique in Europe. But where the type of fibers that are used are advanced fibers. So we're talking about carbon fibers, basalt, glass, PBO, and also steel fibers that are embedded in a cementitious matrix usually. And the issue that we see with using this advanced composite is that rarely we can exploit the full capacity and the full strength of this type of materials, especially when we're considering application on reinforced masonry and in developing countries where the quality of the original structure is low, and going to strengthen that with very high performance materials that kind of seems like an overkill for us. So the drawing from this, and also considering that the natural fibers are produced in many of the countries that are also affected by earthquake, and this would make the use of natural fibers instead as a replacement for high-tech fibers will make them a cost-effective solution, and also a local resource that countries afflicted by seismic hazard can draw upon to develop more sustainable and cost-effective solutions. And so the going to the development of the natural fibers textile reinforced mortar that we used in the study that we'll be discussing today. We've looked at a different type of fibers, but I only focus on two of them today, on flax and jute. And these were used in combination with a lime-based mortar. We chose a lime-based mortar because the lime-based mortar is more suitable to application on reinforced masonry because of the breathability that and the properties that it imparts, and the compatibility with the substrate. And also, it happens that the alkalinity level of the lime-based mortar is much lower, so it gives a better chance of survival to the natural fibers that we're using. There are a few technical challenges and technological challenges that we had to learn along the way. First is that because of the makeup of the yarns and the textile, depending on the level of impregnation that you might have with the surrounding matrix, you have a very complex shear stress transfer mechanism within the fibers themselves and the textile. And this complex mechanism is both between the textile and the matrix in terms of bonds, but also within the single yarns, as you might have that not all the filaments included in the yarns might be activated at the same time, so you don't have a uniform stress transfer within the yarns, therefore within the textile, and this can change the mechanical response and make also even a bit more complicated the characterization of the mechanical properties. And then we, because we're dealing with textile, we need to consider the makeup or the architecture of the textile, including the spacing between the fibers, the yarns, the diameter of the yarns, the angle of twist of the yarns, and the way that they are interwoven. And then when going into the application, we need to consider how many layers of textile do we need to apply to be able to develop or to guarantee a certain minimum reinforcement ratio that can enhance the performance of the structure that we're going to strengthen. And also, how well is the composite, is this textile reinforced mortar working with the substrate? And also dealing with the variability of the fibers, as I explained earlier on. And all of this in a situation where we still don't have standardized methods to characterize this type of material, especially for structural applications. So we had to draw from standard methods or techniques that are generally used to characterize textile for or natural fibers for textile, as in clothing applications or other applications that are not pretty structural. So they are not looking at the same properties, characterizing the same properties as we require in structural applications. So we've set out to explore all these, the opportunity that natural fibers can provide. And we've devised an experimental program that is made up of 3 phases. First phase, where we wanted to characterize the mechanical properties of the textile, starting from the fibers, the individual fibers, all the way to the textile, and then test or assess the bond performance with a masonry substrate. So creating our textile reinforced mortars, bonding it to a masonry substrate, and determine the compatibility between the 2 systems and how they work as a composite. And then finally, we attempted a full-scale structural strengthening of a masonry wall subjected to in-plane shear. So to have in mind, again, seismic strengthening as main application of this type of materials. And also with the view of trying to develop design and test recommendation that can be used for characterizing this type of material for structural applications. So I'll go through the different phases of testing, highlighting what I think are the interesting points, and then I'll draw some conclusions. Starting from the first phase, where we did the characterization of the materials. So as I said, we've looked at characterizing the materials at the multi-scale level, meaning from the fibers all the way to the textile. And we did a series of tests on single fibers, on single yarns, as well as on the textile themselves, and also on the coupons made with one layer of one or multiple layers of textile embedded in the lime mortar. So as I said, it was a challenge to do these different type of tests, also finding the appropriate equipment to develop the appropriate strength, because we're not talking about very high loading capacity, and some of the machines in our heavy structures that were not really fit for testing small fibers. So we had to borrow some of the material from the materials department. But in a nutshell, when we go and test the single fibers, this is the stress strain behavior that we obtained. So a linear elastic behavior as we were expecting from the single fibers, with quite a lot high tensile strength capacity, which is encouraging in terms of structural applications. Unfortunately, things don't stay the same when we go to a higher scale. So when you look at testing the single yarns, which make up eventually the textile, from a strength of about 800 MPa, we go down to a maximum of about 400 MPa. And so testing the single fiber doesn't, well, gives an indication of the strength of the material, obviously, but doesn't give you a correct strength that you can use for structural, for the design of this element or this material in structural applications. And the major difference between the single fibers and the text and the yarns is given by the architecture of the yarns, and the fact that when you're producing yarns, you are putting together fibers that are not unidirectional and with infinite length, like you might do for advanced composite. So the architecture of the yarns itself, so the weaving pattern and the twist angle, the diameter of the yarn, all make a difference and affect the resulting mechanical properties. And also you can see that from a linear behavior, we go, when we have a yarn, we go to a initial hardening phase and then to eventually to a linear behavior, where this initial phase is given by the straightening of the fibers when we apply the load. So again, that is something that needs to be considered, because the depending on the application, maybe applying a little bit of pre-stress when these type of element materials are applied to the are embedded into the mortar, will enable to exploit the stiffness, the higher stiffness, for much lower loads applied to the structure. When we go to testing a textile in uniaxial tension, which is typical type of test that you will do to characterize the material strength, again, we notice a difference between the tests on single yarns to the text of multiple yarns laid out in a textile, and this is because you have it's fairly difficult to evenly distribute the load between all the yarns. So you will have some of the yarns working more or less than the others, and this gives an overall structural response that can be affected by geometrical properties of the textile itself, which will need to be embedded in eventual standardized tests for the characterization of this material. When eventually we embed these natural fibers in mortar, then we see typical behavior that we might see in advanced composite textile reinforced mortar. But obviously we are dealing with different level of strength and stiffness provided by the materials. And one important aspect that kind of links the proper characterization of the material properties of the natural fibers to the response of the textile reinforced mortar is the accurate or the reliable characterization of the geometrical properties, so that we can work out what the critical reinforcement ratio that should be provided to the mortar or to the cement or to the mortar matrix is to be able to obtain a proper composite behavior. And that is a challenge. So if you provide too little material, then your mortar will dominate the behavior, and you're not really utilizing the fibers that you're putting in your mortar. But if you do provide an appropriate amount of reinforcement, you have multiple cracking, so a development of a good composite behavior, and the composite that can be used in structural for structural purposes. So we've done a few tests to look at the amount of material, amount of layers that needs to be included in textile in lime-based mortars to make up a good composite. And we came up with a number, with the minimum percentage of mechanical ratio that we should have, but obviously it depends on the type of fibers and the architecture of the textile that is testing. So we can't really generalize this as the minimum mechanical reinforcement ratio that should be used for all the textile, for all natural-based textile. We also looked at the effect, again, playing with the reinforcement ratio, the effect of overlay thickness of the mortar, in an attempt to also minimize the amount of mortar that should be used to obtain an appropriate composite behavior. So after this, we've, in a way, we selected the best type of natural fibers that was given the optimal mechanical properties that we wanted from the composite. And we started doing some bond tests of this textile reinforced mortar to masonry substrate, exploring the textile architecture. So we decided that flax was the best type of natural fibers to use. We had two different types of textile with different yarn diameter and spacing, different weaving patterns. So we tested it looking at different bond length, try to determine the minimum bond length that will develop, that will enable the development of full strength, and different type of textile layers, to see the bond not only with the substrate but also the interlayer bond between the different mortar matrices, mortar and textile layers, and also the bond width to again decide to assess what the main design critical parameters could be. And this is summarizing the results for the textile with the larger spacing and the wider, the larger yarns in terms of diameter. And we can see that the addition of the increase in bond length does help in increasing the maximum load that can be developed. But again, the load that could be developed was not high in terms of structural performance. And that was mainly due to the large diameter, well, the architecture of the textile and the large diameter of the yarns. And because they had the larger diameter meant that they were not well impregnated and not well bonded throughout the whole cross section to the surrounding matrix. So we have quite a lot of sliding within the yarns that will impair the performance. Was the second type of flux with the smaller twisted yarns and with the smaller spacing was able to develop much higher tensile strength before at the bonding, so much higher performance. But the main issue with this could be that because of the dense layout of the yarns, you could have problem of impregnation between layers, so you could have delamination within the layers themselves. So, which can mean that more than 2 or 3 layers might be impractical and probably not necessary and will lead to different type of problems. I can probably skip this. It's just to show how the bond slip test work and how the concentration of stresses might work along the bond length. But in terms of determining an effective bond length or an optimal bond length, we saw that for this type of textile, about 200 millimeter is able to develop the full strength. And also that smaller width of textile reinforced mortars work better than larger width, but this is mainly because we can engage all the fiber, all the yarns across the textile in a more uniform way and exploit their strength more efficiently. I will skip this because it's more mainly due to some experimental issues. And I will go to the last phase of the project, which is really to test the effectiveness of using this type of material for strengthening real scale elements. So we tested unreinforced masonry walls in plane shear. So we have, this is the wall panel, and we have a load applied, or an horizontal load applied to the top. And also we're trying to restrain the vertical movements of the top of the wall to enforce a proper in-plane shear behavior. And we tested a bare wall for reference, and also we tested a bare wall with only lime, a lime layer so that we could determine the real contribution of the textile. And we performed several tests, and this is a summary of all the results, where we can see that the bare wall fails by developing very discrete diagonal cracks, as expected along the joints of the mortars. But was when we add the lime-based mortar and the lime-based mortar reinforced with natural fibers, we can develop a much more uniform distribution of strain along across the specimen. So we have a more distributed cracking, and we can increase the energy dissipation capacity. This is probably more evident by this summary graph, where we have energy dissipation capacity that increases with the number of layers that we added to the mortar. The maximum crack width that we measured during the test again, which was restrained much more effectively by at least adding 2 layers of the natural fiber reinforcement, as well as the deflection of the top deflection of the wall, which was more controlled from the when adding the external reinforcement. So in conclusion, we're fairly happy to see that this type of natural fiber textile can successfully be used to create effective textile reinforced mortars as an alternative to the more costly and high-tech fibers, and they can also be used to successfully strengthen unreinforced masonry. They can provide, they might not be able to increase the strength of this type of elements by much, but they provide structural integrity, and they enable a better distribution of strain and cracking, and they can control the brittle failure modes of the unreinforced masonries. So there are, we see quite a lot of opportunity, but obviously there are issues. And as I had in the previous, one of the first slides with the issues revolving around durability, moisture absorption, and problems with in alkaline environment. These are some issues that we are currently working on, and also within the one of the new RIIE-WU committees that have been established, looking at durability of textile reinforced mortars. And we are also, as part of that study, we're including natural fibers. So there's quite a lot of work that is being done as we speak on durability and long-term behavior. But also main challenges are needed to be addressed in terms of the characterization of this type of material, given the high variability that we have because of their natural nature, and which is something that we really need to address if we wanted to use them as structural materials. So this concludes my discussion or my thoughts on the use of natural fibers. If you have any questions, I'm happy to take them.
Thank you, Professor Panatini. Any questions from the audience?
Yeah, I've got question. Well, there are some questions in the chat box as well, but for myself, yeah, I think it's yeah, thanks for a nice presentation and also having the good streaming material embedded in cement mortar. I'm thinking that do you consider something like fire or insect biting, thing like that or not? Because in Thailand, it's
yes,
smart. Yeah.
Yeah, that is a good question. I mean, the fire issue is always going to be an issue. The idea is that the fibers are protected by the lime mortar, but obviously you do have you might have issues at high temperature. Now, depending on the application that you have in mind, it might be an issue or not, in the sense that if you're using it for the strengthening application that I discussed here on walls, yes, that would be an issue, because obviously the natural fibers are very sensitive to elevated temperature and they can degrade. So the only thing is to protect them like we will do any other advanced composite. When it goes to using this type of fibers as short fibers in concrete product, it will be actually an advantage, in the sense that if as long as we have fibers in the matrix that can create channels for vapor, the vapor pressure to escape once they are melted, then we still achieve a good properties and enhancement of spalling resistance.
Right, thanks. Okay. I think there are two questions in the
yeah, I can see one question is about why lime-based mortar instead of cement-based mortar. So the choice of the lime-based mortar instead of the cement-based mortar is that the lime-based mortars are more compatible with masonry substrate, and because they allow a better evaporation of the moisture from the masonry, whilst the cement are more dense, and they can damage in the long term the underlying masonry. Yes, and in strengthening application on masonry is actually not allowed to use cement-based mortars, or at least if there is any cement, the content needs to be very low. to avoid any issues to the substrate. The other question.
We have more questions on the chat, Professor.
How would the open mold layup technique affect composite strength? And have you ever tried using recycled jute fibers? We haven't tried to use jute fibers for the open mold layup technique. I guess the main issues is really controlling the stress in the fibers when you lay them, and making sure that they're straight. So there are issues, but I guess the issues with the pre-stress or this, I guess, is a choice that needs to be made, where you want to pre-stress them or not. But we think that pre-stressing them will make them work more efficiently, because at the beginning of the stress strain curve on the textile, you have this non-elastic behavior with very low stiffness offered by the textile, because the fibers are still stretching. So you need to make sure that the textile is stressed to a point that you are engaging the higher stiffness from the very beginning of loading. This is something that we are also working a bit more on, but that's what we think. For the recycle of the jute fibers, I guess if we can make a textile and we can characterize it, then we can reuse it.
Okay, thank you, Professor. So I think
I think I've addressed all the questions on the chat, but let me know if there is any more.
Yes. If any audience have some more questions, you can contact Professor Mauricio later. Okay.
Okay, thank you.
Thank you.
So next will be a short break for 5 minutes, and we have Mauricio as the chairman and Professor Vanasili as the co-chair. So we see you, I think 3 minutes left, 5:45. Okay. Okay, we are back now. Right. So for the next section will be technical section 2, engineering risk reduction, strengthening, and management, and also the technical section 3, advanced composite in civil engineering applications. So we will have Mauricio. We get to know Mauricio. He was one of my supervisor back in Sheffield about 18 years ago. His face still look very young. That surprised me a lot today. And we also have a nice lady professor, Dr. Wanasiri Panurai. She obtained her PhD from Georgia Institute of Technology back in 2006, and also her specialized for in the area of strengthening of RC structure, FRP, and non-specific testing as well. So I will pass all this to the chair and co-chair, please.
Thank you, Dr. Danusa. So the first speaker for this session is Dr. Chayanon Ansapinho. I hope I pronounced that name correctly. He's an associate professor at the Department of Civil Engineering, Chiang Mai University in Thailand, and has 20 years of experience working in teaching and research. He got a bachelor degree in civil engineering from Chiang Mai University, and a master of and doctor of philosophy from Sirindorn International Institute of Technology in Thailand. He specializes in concrete structural responses under extreme loads, including, and he does both experimental and numerical simulation. And his presentation today is about reinforced concrete beams under sequential impact loads. Please, Dr. Chayanon, if you
hello. Can you see?
We cannot. I can see a blank screen. Okay, now it's coming. Okay. Yes, okay. It's all good.
Thank you very much for your introduction. And I would say, Swaddi to the all participants living in Thailand, and also good morning to some of you that are living in UK. And today my presentation is about reinforced concrete beams under under small sequential impact loss. Sorry that the screen is it's moved to the second page. Can you see the second page?
Yeah.
Okay. First, I would like to address why do we need to understand the impact response. Normally, we design our structure to resist the static load, like dead load or live load. But in some situation, the structure will be subjected to impact load. For example, like a car crash, blast load, and also building pounding. The impact loading is the loading condition that generates high intensity of force within a very few milliseconds. The high loading rate causes the behavior of the concrete to change. As you can see, the relationship between the stress and the strain of the concrete when subjected to the compressive loading. When we increase the strain rate from the 290 per second to about 1,500 per second, the shape of the stress strain changes drastically. And this one is one of the results that when we apply the static load on the beam, we can get the failure mode in fracture. But if we apply the impact load, the failure mode change to the shear failure. And the second one of the high load intensity and high loading rate is that they have some initial effect. I would like to explain the effect of the initial by considering the force distribution between the applying static force at the middle span of the simple beam. We can have the shear force diagram like this, and also the moment diagram like this one. But for the impact force, we have the initial effect distributed along the beam length in this shape. So in the early state of the equilibrium of force, there are some different, especially in the force, shear force distribution change a lot from the case of the static force. And also the moment distribution also change. In this lesson, we can use to explain that why we decide at the beginning that the beam will be failed by fracture, but it changed to the shear failure if it's under the dynamic impact. Next, I would like to explain the response of the reinforced concrete beam subjected to the impact loading. The response, we can see it from the graph between the force in the vertical direction and also the time. We call it as the time history. In the time history, we divide it into two phases. The first one, we call it early stage. In the early stage, we can see the local response. We have the very high stress in the impact point. And if the impact load is very high, we will have the failure in the impact location. And also we can have the failure, so-called the shear plug failure. And when we look at this graph, the early stage can be defined from the 0 to about 2 milliseconds. And after that, we call it steady state, in which the beam will respond in the overall response. And we can see that from this graph, we have three forces. The first one is the impact force indicated in the red line. And the second one is the reaction represented by the black dot line. And the third one is the acceleration represented by the green dotted line. So we can see that at the early state, the reaction almost 0. It means that the initial force, the green line, is very important. We have to consider. This slide shows the effect of the impact velocity by the study of Dr. Kishi in 2002. They have 8 beam specimens that divided into 2 groups. The first one, the specimen designed for the shear failure because they have the shear to moment strength ratio about 0.64. And the second group, they decide to fail by bending failure, indicated by the shear to moment ratios more than 1. And all of the beam were impacted by vertical load impact loading at the midspan and increased the impact velocity from 1 meter per second to the 5 meters per second. We can see the difference from the failure of the 8 beams, and we can conclude that if we increase the impact velocity, the failure will change from the fractional failure to the shear failure. Next, I would like to explain you about our study on the reinforced concrete beam under small sequential impact loads. Why we understand this? Because most of the past research, they mainly focuses on the impact resistance under a large single impact force. There is just a few papers mentioned about small and repeated impact loads. But in some cases, structures are subjected to lighter and occasionally repeated impact loads without causing significant damage. In my study, I conduct 6 small sequential impacts, and finally, I determine the residual capacity of the impacted specimen. I would like to explain about my study. We made all the beam totally 12 specimens, and all the specimens have the same dimension and also the same cross-sectional dimension. The variable are the level of the axial load, change from 0 in percent of the AG and FC prime to the maximum one about 0.28 of the AG FC prime. The next parameter is we change the spacing of the stirrup 100 and 200 millimeter. All the 12 specimens we divided into 2 series depended on the loading scheme. In the series 1, we have 8 specimens, and all the 8 specimens are subjected to the sequential impact load at the midspan. For the series 2, the remaining 4 specimens, we test it under static load at midspan. Anyway, we want to know that the impacted specimen in the series 1. We would like to determine the residual capacity of the series 1, so we take it to test for the ultimate static load capacity, and then we compare the strength between the specimen that test under static only and the specimen that already test the impacted and then test the static to compare for the residual capacity. Under the impact load for the specimen in series 1, we conduct 6 small sequential impacts. The first 2 we drop at the height of 0.35 meters. And for the next third to the 6 drops, we increase the height to 0.7 meters. But we keep the drop weight of 300 kilogram. This slide shows our test setup. We use the steel tower to guide the load. The dropping weight will attach to the steel tower by using the roller, and then we drop it to our specimen here. We have measured the midspan deflection and also the deflection in the third span also, and also we measure the acceleration. Next, I would like to talk about our result. I select 2 specimens to explain the impact load time history. The first one is the specimen that they don't have any axial load, that we call it specimen number I00-1, which means that this specimen are subjected to impacted load without any axial load. And the second specimen is I28-2, which means that this specimen are subjected to impact load with the axial load of 0.08. In the graph, they show vertical load for the impact force and the time series. We have 6 impact. This is the first impact, the second impact, and the third, the fourth, and the fifth, and the sixth. And we measure the impact force that occur after the collision. We have the peak impact force. And we can see that after we increase the doping height, the impact force will be increased. But we can see that for the specimen without any axial load, the peak impact force drop from the third. For example, the peak impact force in the third drop is about 323 kilonewton. But for the fourth drop, the peak load was lower to about 190. We can explain this because there is some damage when we impact the third impact damage the specimen. So the impact force for the fourth and the fifth and the sixth reduced. But for the specimen with,
please. 2 minutes.
Okay, so hurry up. For the specimen in the with the high axial load, we can see that there is no drop of the peak impact force, which means that there is no damage. And this one shows the strain that we install in the reinforcement. We can say that when we more impact will increase the strain. And this one also the strain in the stirrup. When we the more impact will increase the strain of the stirrup also. But we can see that in the case of when we increase the axial force, the strain will be decreased. And also we observe the crack propagation from the test in the series 1. And when we finish the impact test, and we bring them to test for the ultimate static load test. And we can plot the ultimate capacity, and we compare the ultimate capacity with the undamaged specimen. And we call it as the RRI, or the residual index, residual capacity index. So we can see that when the impact to the specimen, the capacity will be decreased, especially for when we increase the axial force. And finally, I would like to conclude my study that the repetition of the impact deteriorates the impact response. So the increase of the strain in the reinforcement and also increase the crack propagation. The higher axial load results in better impact performance, but decrease the residual resistance index. And the RI index should be considered for some structures subjected to small repeated impact loads. For example, the bridge column or the quayside, to check for the residual capacity to be larger than the sustained service load. That is my conclusion. Due to the limited time, I think I cannot say all the things that I would like to present today. But we have published the result in the international journal, and this one is the International Journal of the Structural Stability and Dynamics. So we can look at this paper for more information. And also this one we publish in the Buildings Journal. That's all my presentation.
Okay, many thanks, Professor. Very interesting presentation, many thanks. Is there any, we have time for one quick question. If there is any question from the audience? I don't see any raised hand, but. So if there isn't any question, I'd like to ask one quick question, I think. Just a curiosity, I mean, it looks like a fairly complicated text. And I was wondering how much effect on the total response has the restraint level that you provide at the end. And if that changes with different impacts.
Mm.
Can you say again, Mauricio? I don't think he can hear you.
Oh, sorry, again, please.
Oh, you did? Okay.
Okay.
Do you want me to repeat the question or was it clear?
Yes, again, please.
Okay.
Hello?
Okay, maybe we can take this offline.
Okay.
Thank you. So we can move to the, can you please stop sharing your screen so the next presenter can share theirs? Thank you. Okay, so the next presenter will be Professor Cristina Barris from the, Cristina is an associate professor at the University of Girona in Spain. A research interest fall in the area of composite structure, reinforced concrete, and serviceability of reinforced concrete structures. And today she will be presenting her work on fiber-reinforced polymer for reinforcing and strengthening concrete structures, looking at flexural and serviceability behavior. Cristina, please, when you're ready.
Hello, can you hear me well?
Yes, and we can see the presentation.
Okay. And the presentation is okay? I cannot.
Is in presentation mode, yes. Yeah.
Okay, thank you very much. Thank you for your kind introduction. Good afternoon or good morning, depending where we are. As it was presented, my name is Cristina Barris. I come from the University of Girona in Spain. And today I would like to talk about fiber-reinforced polymers for reinforcing and strengthening concrete structures from a flexural and serviceability point of views. Okay, so the presentation is separated into these 5 points. So basically, I will give a very short introduction to FRPs. Then I will talk about 3 applications of FRPs. So the first one will be concrete flexural elements reinforced with glass FRPs. Then I will move to some contributions in the field of concrete flexural elements strengthened with a technique called NSM with carbon FRPs. And then I will mix both strategies. So glass FRP reinforced concrete beams strengthened with this technique NSM with CFRPs for arriving to some conclusions. So as all of us know, in civil and building infrastructure, concrete structures can suffer from, along their service life, from maintenance problems due to several reasons. Among them, we can find aggressive environments, increase of their loading requirements, etc. So in these situations, FRPs have appeared as an excellent solution because of their their mechanical and other properties. In this slide, we can see different shapes of FRPs, so they can be presented like bars or plates or laminates, strips and grids and sheets. Just a short look at which are the mechanical properties of the FRPs. Mainly, we know that they present typically higher strength than steel. Their behavior is linear until rupture, which make them, this is the failure mode that we usually face with FRPs. For the ones that are with glass fibers, the modulus of elasticity is relatively low, and they provide different bond properties differently to the steel reinforcement. So according to the two applications that are mainly used, FRPs can be used as internal reinforcement for concrete in the cases of we face aggressive environments, or we want to look for electromagnetic neutrality, or we want applications that need to be easy demolished, or also for low thermal conductivity. On the other hand, when we want to use FRPs for strengthening, we can see here flexural strengthening using one technique. It's called EBR, or another one, shear strengthening, or the column wrapping for confinement. So we are looking more for properties like the lightweight, or their high strength to weight ratio, or durability. FRPs can be typically placed in strengthening methods into several methodologies. The first one is the externally bonded reinforcement, which I will call it as EBR, or the near surface mounted, in which a relatively small strip is introduced in a groove that is previously cut in the cover of the tensile face of the beam. So now I will move to the first part of the talk, which will be some contributions that in the University of Girona found regarding the flexural behavior of concrete elements reinforced with glass FRPs. So in this case, what we wanted to see was the overall flexural behavior of these materials when we substitute the concrete by them. For that, in that occasion, we performed an experimental program in which we wanted to obtain a wide range of the deflections, and we tested 27 beams with several instrumentation. So we had strain gauges in the two materials, we had several transducers, inclinometers, mechanical extensometer, etc. The main things that we found were that, for example, this is the concrete strain at mid-span, only in the strain gauge that was on the top surface of the beam. So effectively, as we were expecting, the higher the reinforcement ratio, the higher the D over H ratio, which was another parameter, and the higher the concrete strength provided the lower concrete strain. Another thing that, here we compared with the cracked sectional analysis, and more or less good results were obtained. Another measure was the curvature in the midspan, and we obtained it by several strategies in experimental field, and in all of them we provided also good results. Finally, the deflection at midspan could be seen that it could be calculated in several ways. So simply placing the transducer and comparing it with the crack section analysis, we can see that the deflection was higher for high loads, while it was more or less well predicted in service range. And inclinometer, so it means integrating the curvature along the beam, it provided less deflection, meaning this would be the flexural deflection, and this will be the total deflection. Another effect that could be measured was the tension stiffening contribution. In this case, we placed several strain gauges on the tensile reinforcement, so we could measure an effective modulus of elasticity as the ratio between the strain in the cracked section divided by the average, the stress in the cracked section divided by the average strain along in between cracks. So if we divide this modulus of elasticity, effective modulus of elasticity, by the actual modulus of elasticity of the bar, we could see that there was an area under this curve that in a way provided a measure of this tension stiffening effect. This could be also represented as a stress-strain relationship, which could be easily then provided to implement it in models, in numerical models, to take into account this effect. Okay, another contribution was to see which was the cracking behavior of this kind of reinforced concrete elements. This is another experimental program. In this case, we were mainly interested of measuring cracking in the section that we only had pure bending moment. So we placed a digital image correlation. Consecutive cameras were placed, so we could see which was the effect of different, sorry, here I thought there were more, no, okay, we can see this in this slide anyway. So we had different reinforcing bars with different coatings, and basically here I only showing one of the things that we found, that was that if we are able to find or to characterize which is the bond coefficient that is in this empirical formulation of, for example, the Canadian codes or the Japanese code, we can see that the results say that the bar that has a rivet surface, which we can say more or less that it's better, maybe better than the steel one, effectively provides lower bond coefficients. Lower bond coefficient means lower crack width, so it means better bond performance. While the bar that was was wrapped with these helicoidal fibers provided slightly higher values of the bond coefficient. Okay, let's move now to the concrete elements that are strengthened with near surface mounted CFRP strips. So in this case, this is another experimental program in which we were interested in seeing which was the contribution of these FRPs. In this case, we placed carbon strips inside some grooves, okay? And this is the technique called NSM, as I mentioned previously. And in this experimental program, we saw, well, we had two reinforced concrete beams called reference ones, R1, R2, which were without any reinforcement. So here you can see the typical load deflection curve with the 3 stages, and they eventually failed by concrete crushing after yielding. Then we had 3 more beams that were strengthened. And we can see several things. No, the first one is that if the reinforcement rate, the internal reinforcement ratio of steel is relatively low, we can have an increase of the stiffness. Well, if the internal reinforcement ratio is high, this increment is more difficult to find. Then we obtained always an increment of the yield strength. And finally, there was, well, as expected, as the FRP is working after yielding of the steel, we can have this increment of stiffness after yielding. It should be mentioned here that, as probably also known, these FRP strengthened beams, except for this one, the lowest reinforced one, strengthened one, the other two failed by. One failed by concrete cover separation and the other failed by concrete cover separation plus concrete crushing. So some attention needs to be paid in the bonding failure mode. In this sense, now at the University of Girona, we have started a PhD thesis to study, so to provide some anchorage systems for, in this case, is EBR FRPs, and we hope to contribute in this sense. Another experimental program, also in this case, we were strengthening with NSM FRP, but in this case, the objective was to consistently measure cracking. So we placed again the digital image correlation along the central part of the beam. And in this case, we performed a couple of subroutines, MATLAB subroutines, so we could consistently acquire the crack width along the height and also with time. And here we have an example of one of the cracks. So the aim of this program was not only to study cracking by itself, but to have conclusion on which is the effect of providing a new layer here of reinforcement. In this case, it was carbon FRP. And we obtained, well, the crack width for all beams. Here you can see that some things are happening. So some cracks still appearing after the cracking moment, no? And if we have a look at all beams at a given service load, in this case was estimated to be around 30 kilonewton. these are all the beams with the n row ratio being n the modular ratio, so modulus of elasticity of FRP divided by that of the concrete. We can see that we had a clear or almost pretty clear descending trend, as it would expect it, for we have more contribution of FRP when we are increasing this ratio. And here we can have a short video of how these cracks were created, and it can, well, we can have a better knowledge on how they are created. Here also we can see how the load crack width keeps evolving with time. And for us, something that was relevant is that cracks continue appearing between the cracking moment and yielding. So we have cracks appearing during all the process of loading. This is different from where we know from steel reinforced concrete structures, in which we have the typical cracking formation phase and then the stabilized cracking phase. No? So here we could not arrive to a stabilized cracking phase. Okay.
Okay, Professor Christina, 5 minutes. Actually, less than that.
Okay, thank you. I think I will manage, because I'm going to the last application, so and it's very short, because here we wanted to take benefit of beams that were internally reinforced with GFRP and were tested until their service load, and then we strengthened them with NSM. So we wanted to say if this combination could work in flexural. And this is the last slide. So here we can see that this is the load mid-span deflection of 4 of the specimens. Of course, we cannot notice here the uncracked behavior because the beams were already cracked, but we can see an effective increment of stiffness due to the contribution of NSM. But as we increased the load, this deflection, so again, there were other effects taking place. Furthermore, there was a premature failure due to a nice concrete cover separation that we had in one beam. So the last one, we decided to strengthen in shear, in which, and then we could see that these effects disappeared, plus we did not have a premature debonding failure. And then I come to the conclusions. I don't know if maybe we can have a quick look. So for the GFRP reinforced concrete beams, due to the modulus of elasticity of the glass, they might be designed by serviceability rather than ultimate. And the deflection and ultimate capacity can be calculated using the typical sectional analysis, while crack width may depend on the bond properties of the FRP bars. If we go to reinforced concrete strengthened with CFRPs, we can see that FRPs effectively provide this enhancement in first in strength and second in stiffness, but we need some devices to avoid this debonding. And mainly cracking depends on the N-row ratio, and we have these large crack formation phases. And finally, these GFRP reinforced concrete beams strengthened with NSM CFRP. We can see that one thing I didn't mention in the presentation is that we need to be careful because strengthening may eventually change the failure mode, leading to a more fragile failure, and then that sectional analysis reproduces well the deflection at a service level. While at the higher loads, this experimental deflection might be underestimated. Thank you for your attention.
All right, any questions for Professor Christina? Any question? Due to the long program, I think I will take up the stage and introduce to all our next speaker. Thank you, Professor Christina.
Thank you.
If
Okay,
there is any question, you can just put in the chat box, then we can have a look at it later on.
Okay, thank you.
Do we have any breaks, or should I continue, Dr. Thanongsak?
Yes, please.
All right, I'll take up the stage now. Welcome you all to the technical session 3, Advanced Composites in Civil Engineering Applications. let me remind you that we have the long technical sessions following after this one. So please keep in mind that you have only 15 minutes to present and followed by question and answer. Our next speaker is Associate Professor Dr. Sayan Sirimonti from Thammarat University, Thailand. Dr. Sayan Sirimonti is an Associate Professor from the Thammarat University. He specialized in the inspection and evaluation of concrete structures such as reinforced and pre-stressed concrete. His research focuses on the deterioration, repair, and strengthening of concrete structures. He's going to talk about the strengthening of concrete structure elements. Welcome, Associate Professor Dr. Sayan. Please.
Thank you very much for introducing me. Okay, thank you. My name is Sayan Sirimonti from Thammarat University. Today, I would like to present about the overview of my research work I do with my student. The topic is the strengthening of concrete structural element. I will talk about the strengthening of damaged PC pre-stressed concrete beam by external post-tension, strengthening of RC slab by concrete overlay, repair and strengthening of reinforced concrete beam by carbon fiber reinforced polymer plate, and strengthening of RC column by ferrocement jacketing, and strengthening of column strengthened by steel strap confinement. And the last topic will be discussed about the punching shear strengthening of RC flat plate by adding the ferrocement drop panel. Why the concrete structure need to be strengthened? Concrete structures that have been in use for a long time need to be inspected for their condition. If the structure is deteriorated or damaged, leading to the loss of performance with time, it must be repaired and strengthened. This is a performance curve of concrete structure. The structure have to be evaluated and diagnosis and decide how to repair and strengthen. This work is about the strengthening of damaged pre-stressed concrete beam by external post-tension. In Thailand, the truck that exceeds the legal weight may result in cracking of the bridge girder. So flexural stiffness of bridge girder reduced, leading to the excessive deflection. Strengthening damaged beam by external post-tension is an effective method to increase flexural stiffness and reduce the excessive deflection. In addition, to increase the flexural strength of the beam, we test the PC beam in the lab beyond the cracking stage. It can be seen from the figure that the stiffness of the beam is reduced when we apply load beyond the cracking stage. In each step of overloading, we repeat the load for the 10 cycles. And after that, we apply the external pre-stress to increase the stiffness, to increase the stiffness and strength and reduce the excessive deflection. This work is doing about the shear strengthening of reinforced concrete deep beam by transverse external post tension. The the shear span to effective depth ratio is vary from 1 to A over D is equal to 1 and equal to 2. And the beam without strengthening is used as the reference. So we test up to failure. It can be seen from the figure that shear strength can be increased effectively by the external post tension, the transverse external post tension. Not only the strength, but the ductility is also increased, especially for the A over D ratio is equal to 2, as can be seen by the figure. This is the shear strength of the reference beam, and this is the shear strength of the strengthened by external post tension. And for the A over D shear span to effective depth ratio is equal to 1. The increase of the shear strength is significantly increased by the external transfer external post tension. In this work, we study about the strengthening of reinforced concrete slab by concrete overlay. The deterioration of reinforced concrete slab can be caused by overloading due to illegal traffic load, accidental fire damage, or abrasion due to traffic. In this, the left side picture, there is an oil tanker overturned on the bridge and caused a fire on the concrete deck surface. The duration of fire is about 2 hours. Concrete at the damaged bridge surface was extracted and overlaid by high performance concrete. To be confident in this repair method, the composite action between the concrete deck and the concrete overlay was tested. This is a reference slab, and the slab is strengthened by concrete overlay. The thickness of concrete overlay, and the mechanical shear connector is used as the parameter. In the first test series, slab is overlaid by concrete. From the range is overlay is vary from 50 millimeters to 150 millimeters. All specimen, the interface between the overlay and existing slab, the shear connector is provided at the interface of the specimen. It can be seen that load carrying capacity of slab is increased for the increasing of the concrete overlay, except for the overlay thickness is very high. We found the interface slip and brittle shear failure occur at the shear span of the slab. This is the surface slip and cracking due to shear at the shear span of the test specimen. This should be concerned in the consideration and the design how to strengthen the slab using the concrete overlay. In the second series, the overlay concrete is kept to constant to 100 millimeters, and one specimen, the shear connector is provided at the interface but for another specimen, shear connector is not provided. So it can be seen from the load deformation relationship that strength of the load carrying capacity of the strengthened specimen is increased for the strength for the specimen with shear connector, but for the specimen without shear connector, the strength is increased, but we found the shear failure and interface slip at the shear span of the test specimen. From this study, we can conclude that from the test data, we can conclude that the composite action between the top slab and concrete overlay can be achieved by mechanical shear connector, lead to the increase in flexural strength, stiffness, and ductility of the strengthening slab. According to the test data in this work, it can be proposed that the ratio of the overlay thickness to the thickness of existing slab should not exceed the 0.67, and the ratio of shear span to effective depth ratio should not less than 3.57. Otherwise, shear reinforcement should be provided to prevent the sudden failure due to shear. Slab strengthened by concrete overlay without shear connector can be done to increase the flexural strength and stiffness, but the failure mode might be brittle failure due to shear. So further study are needed to be clearly understood about the effect of overlay thickness on the flexural behavior of strengthening slab without shear connector.
Professor Sayan, could you wrap up because we have only 2 minutes left.
Okay.
And we allow 2 questions. I think it's very interesting presentation, but due to the long events and also we have the time difference between UK and Thailand. So
okay.
Please wrap up in 2 minutes and then we allow 2 questions to ask you from the audience. Thank you.
Okay, thank you. I will use 1 minute to finish my presentation.
Thanks.
Okay. In this work, we repair the beam which has a corrosion in the steel reinforcement. So it makes the beam to be unbound between the reinforcement. So we repair by cement mortar. We repair the D-grade beam using the cement mortar, and the specimen in another specimen we repair with the cement mortar and strengthened by CFRP. It can be found from the figure that the D-grade beam, the stiffness of the beam is reduced, and after we repair, the stiffness can be restored and in the original condition. For the specimen with the repair and strengthened by CFRP, the load carrying capacity is significantly increased, and stiffness also. It can conclude from this, from the test data, that the D-grade beam can be restored to their original flexural stiffness by repairing them with non-shrink cement. The D-grade beam repaired by non-shrink cement and strengthened by CFRP can improve both flexural stiffness and strength. And the next is the strengthening of column using the furrow cement, and it found to be that the concrete with furrow cement can increase the load carrying capacity and the ductility. This is a mode of failure of column strengthened by ferrocement. And I did research about the strengthening of column by steel strap confinement. It can, the data from the test is the strength of the column with steel strap confinement is increased, and the ductility of the strengthened column is increased also. This is a failure mode of the column strengthened by steel strap confinement. And I did research about how to strengthen the punching shear using the ferrocement drop panel. We test in the lab and we found that shear strength of the slab adding the ferrocement as a top panel with shear connector, it can improve the punching shear of the slab without beam. That's conclude my presentation. No, that's this is the fact finding from the test of the slabs without beam strengthened by ferrocement. It can be concluded that there are a variety of methods for strengthening concrete structural element. The understanding of the behavior of concrete structure will help in the deciding on the appropriate way to strengthen concrete structural element. Thank you very much.
All right, any questions? All right. I guess it's very bombarding with the information, and your research is very interesting. So I guess anyone who wishes to ask may drop him later in the chat box. All right, your questions. Up next would be our next speaker would be Dr. Thosapon Prasertsi from University of Technology Tawanok, Thailand. Dr. Thosapon is currently a lecturer at the Department of Civil Engineering, Faculty of Engineering at Rajamangala University of Technology Tawanok. Is that correct? And his research interests focus on structural strengthening, structural improvement, and structural optimization. He's going to talk about the bonding of FRP strengthened steel beams. Welcome, Dr. Thosapon.
Thank you very much, Dr. Wansili. Everyone, can you see my presentation slide in full screen?
Yeah, it looks okay.
Okay, thank you very much. Good evening, everyone. First of all, I'd like to say that I really enjoy this conference because the information and insights I gained from attending here are invaluable. My name is Thosapon from RMUTTO, Bangkok, Thailand. I'm here to talk to you about the bonding problem that is frequently encountered and play an important role in fractional behavior of FRP strengthened steel beams. I wish that this short review may give you an insight for further research. We already know that steel is one of the important building materials in construction industry. It can be used in many ways for many purposes. We can see that many structural components are made from steel, such as beams, columns, decking, and joints. When I went to several places, I love taking a photo of steel structure. This shows you that steel structure is around you. Obviously, structural rehabilitation is required whenever the presence of degradation can be detected. Fiber reinforced polymer, actually I can generally abbreviate as FRP. FRP are formed by embedding continuous fibers in a polymeric resin matrix, which bind the fibers together. Common fibers used in FRP composite include carbon, glass, aramid, and basalt fiber. This graph shows typical stress-strain response of FRP composite in contrast with that of mild steel, where it is clearly seen that FRP composite exhibit a linear elastic stress-strain behavior before brittle failure by rupture. In certain applications such as oil storage tanks and chemical plants, where fire risk must be minimized, welding need to be avoided when strengthening a structure. Then bonding of FRP laminate is then a very attractive alternative. I have to remind you all that the main drawback of FRP strengthening is the bonding phenomenon. We will lose a composite action between FRP reinforcement and original cross-section of structural member. Then a structure will cause undesirable premature failure prior to theoretical load level. This reason leads us to discover new ideas for prevention for FRP debonding. Interfacial debonding failure control the load carrying capacity of FRP strengthened steel structure. A simply support steel beam strengthened in fracture with FRP is a typical bond critical case where the debonding failure modes can occur. For the first mechanism, debonding initiates at an FRP plate end due to a combination of high interfacial shear and normal stress we can call plate end debonding. On the other hand, debonding initiates away from the FRP plate end and at a location where high interfacial shear stress arises. For meter the presence of a defect, maybe defect or crack or local yielding of the steel substrate. Intermediate debonding has been observed in laboratory tests. I tried to find literature and specification, and I faced with the lack of an appropriate approximation suitable for debonding of FRP strengthened steel beam. Then I think this field should be conducted because the previous study and practical specification had few exploration of debonding initiation, especially intermediate debonding. Additionally, FRP debonding prevention techniques should be investigated. For the practical purpose, I think a simplified modeling strategy is beneficial to save computing time. A key factor controlling the behavior of metric structure strengthened with FRP is interfacial behavior between FRP and steel that have many different experimental setups for investigating the bond-slip relationship. This is we can call double lap joint test. We just apply tension directly to the steel plate without any gap. It seemed that such testing method was more suitable for studying strengthening rather than the investigation of bond behavior. The literature said that. There is a few literature determine a bond behavior through double strap shear test. Tension was also directly applied to the steel plate with a gap. But I think the single lap shear test as present here is the alternative testing method for the investigation of FRP steel joint behavior because only one path for debonding is possible. Unlike the double strap joint that there are 4 possible locations exist for the propagation of debonding. However, this testing method must be sure that the alignment is maintained to minimize load eccentricity. Adhesive could be categorized as 2 types by adhesive tensile test. I will name the type 1 as linear adhesive, like Dr. Fernando designated. For the type 2, obviously, we call non-linear adhesive. According to the linear adhesive, it denotes the regular adhesive that seems to linear behavior when subject to tensile load, like this. There are other kinds of adhesive that behave non-linear in tension and has a high strain capacity. If we perform lap shear test, collect strain data, and try to plot shear stress versus slip displacement, we will find that the relationship obtained from 2 types of adhesive are not identical at all. At this point, bilinear curve and trilinear curve can be fit quite well with linear adhesive and nonlinear adhesive, respectively. Many adherent, steel members, require surface preparation beyond simple cleaning. There are many reviews point out that the surface preparation is related to bond-slip relationship of FRP steel interface. There are some of the most common methods for improving steel surface bonding characteristics. For the first method, a volatile solvent such as acetone is often used to remove dirt an inorganic solid on a surface. In case of gliding, mechanical abrasion loosens the surface and remove the weak surface layer, then providing a chemically active rough surface for adhesive bonding. The available methods of mechanical abrasion including gliding using abrasion pad and wire brush as shown in this animation. According to the third method herein, shot blasting introduce grit, or maybe we can call particle, residue to the surface, then altering the chemical composition of the surface. Is it important to select a particle type which is chemically compatible with the adhesive? The size of particle used in shot blasting may have a significant effect on surface characteristics. This is SEM analysis. SEM stands for scanning electron microscope, I think. Visual inspection of this surface profile show that the shot blast surface have pore pattern that are more densely distributed than the solvent clean and the hand glove surface. We found that the hand glove surface shows scratchy finish because we use a grinder. But this build pattern of pore are not seen. Even on the solvent clean surface, some scratchy pattern can be observed. This section, I will collect a photo from literature to shed light on failure of FRP strengthened steel beam. I'll start with this work. The author conclude that the beams had two types of failure mode, depending on FRP bond length. Short FRP length induce plate end debonding, while plate rupture at midspan is occur when beam in beam with long plate. It means that plate rupture. It means that FRP activate full. They utilize fully mechanical the mechanical property. Yeah. Okay. The next work also found that debonding failure was observed for the strengthened steel beam bond with short FRP plate. Local buckling had significant influence on both the load capacity. Additional shear steel stiffener were found very effective in constraining local buckling and fulfilling better usage of the FRP plate. It means that if we add stiffener, it means that we may not use longer FRP bond length like that. Okay, I will bring you all to explore different debonding behavior on FRP strengthened steel beam. It seems that anchoring the end of FRP plate decrease the effect of peeling on debonding at the end of FRP plate. Then this work apply a clamping system at plate end. The system consists of a single plate with 4 bolts. The steel plate was placed below the FRP plate and held in place using bolts that were inserted into hole that were produced through the bottom flange thickness as desired location. The failure mode of beam specimen changed from plate and debonding to intermediate debonding.
Dr. Mai, you have 5 minutes. Please wrap up.
Thank you, Ajahn. Actually, from my perspective, I think there are another cause of intermediate debonding, such as poor craftsmanship during FRP installation process and improper surface preparation. So I would like to participate in this field by conducting a simple experiment. I will not go into detail because too many literature exists to figure out how to design and implement such experiment. Today, I would like to show how FRP debonding caused a sudden failure of a strengthened system. Let's see together. Okay, we already see that this is a sudden failure of FRP strengthening system. So I will give you all one more chance with 5-second countdown timer. Let's watch carefully and take a guess in your mind. I will tell you after the second video stops. Actually, I know that the answer is intermediate debonding, but in my view, even though I prepare a 5-second countdown timer, a catastrophic event like this is also difficult to classify as either plate end debonding and intermediate debonding. We have become aware of this potential hazards due to a calculation error and improper selection of method for predicting FRP debonding. Okay, I will only point out the outlooks instead of a series of conclusion. Well, externally bonding of FRP reinforcement has been clearly established as a promising alternative strengthening technique for steel structure by existing research. It is recommended that future research should address the issue with priority like this. Maybe more work should be conducted on the treatment of steel surface preparation and characterization to develop a widely accepted procedure for use in practice that can avoid addition failure. We know that the weak link is the adhesive layer, then provide addition failure at the adhesive steel interface, and FRP adhesive interface can be avoided through appropriate surface preparation. To maximize the effectiveness of FRP strengthening, the selection of an appropriate adhesive is very important. Debonding failure are the most challenging issue. More work is needed to develop accurate bond slip model. Several other topics to have been explored and should be given due attention in the future, maybe durability problem or fire resistant problem, or maybe corrosion protection problem like this. Okay. And I really appreciate Dr. Thanomsak and Walailak University for hosting me here. Thank you very much for your kind attention. สวัสดีครับ
All right, that's great. Nice video of the bonding failure. Thanks to you. And any questions from the audience?
Yeah, I've got a question.
Yeah,
I think it's really nice presentation and video. One thing I just worry your LDT in the last video there, and it's really expensive. And I'm curious about the well, preventing the bonding. You have many different techniques combining chemical and mechanical anchorage. Because you don't really show much about the deformation. I want to see really the strength and on the steels and the FRP, how it's go.
According to the strength, actually I record strength data and midspan deformation. Actually, according to my previous work, is found that if I add imperfection in my beam, it's shown that my beam can change the failure mode from FRP plate and debonding and FRP rupture to intermediate debonding. And surprisingly, is the result got me that the maximum load is more than the case that without imperfection. It makes me surprising.
Okay, thank you.
I guess it will be this section will be end, and next section will be the computational mechanics and structural dynamics. Dr. Thanomsak, I'll give it over to you. All right, thanks.
Thank you, chairs and all presenters in the last section. So the next technical section, visit technical section 5, will be computational mechanics and structural dynamics. The chair will be Professor Suchat Lim Katanju and Dr. Fabio from Minho University, Portugal. So I pass on to Professor Suchat for this section, please.
Hi, everybody, and say good evening and have a very good afternoon to the European audience. Can you hear me? Can you hear me?
Yes.
I will be co-chair with Dr. Fabio, right? Ciao. Yeah.
Oh, Dr. Fabio will use, and you can share your screen right now while he's presenting yourself.
I will be sent first, right?
Yes.
I will be the first speaker.
Yes.
Right. So, should we start, Dr. Thanomsak? Okay.
I'm supposed to introduce you, but as you are the first presenter, I don't have your bio here. You can present yourself.
Yeah. Can you hear my can you see my presentation?
Yes.
Yes.
My name is Suchat Lim Katanju from Songkla University, Thailand, and I would like to say thanks to Dr. Tharongsak for inviting me to be a speaker of this event. And my topic of the topic of my talk today will be on the Euler-Bernoulli beam element based on modified strain gradient elasticity theory. Okay, and first I would like to show you the content of my talk today. And the first one will be the governing equation of the modified strain gradient beam model. And the second one will be a displacement-based modified strain gradient beam element. And the next one will be I will show one numerical example, and I end up with the conclusion. And this study is a very early stage of my new explore of the nanomechanics kind of things. Okay, and let's look at the why we need a small beam. The beam that can account for the small size and nano size beam. And these tiny structure have an application in the micro and nano electromechanical system, atomic force microscope, and nanotubes. I show you some example. For example, this figure shows the ultra high frequency MEMS resonator for electrical contact. Okay, this part can be modeled as a beam. And another one is the ultra high frequency high Q free beam MEMS resonator, and this part can be modeled as a beam. And the last one is atomic force microscopes, and this part can model as a beam. Okay, and in this study we will unify Euler-Bernoulli beam theory with the modified strain gradient elasticity theory. Why do we need this unconventional beam model? Because due to the small scale effect that inherent to microsite and nanosite system, conventional beam model fails to account for this effect. Why? Because the size of the beam is comparable to the distance between atoms. That's why we need some kind of the modified elasticity to account for this phenomenon. Okay, and in this study, I will employ the modified strain gradient elasticity theory that developed by Lam and his co-worker. What is the strain gradient? The strain gradient elasticity theory asserts that the state at a generic point is described as a function of local strain and strain gradient at that point as well, to account for the nanostructure dependent phenomenon, such kind of things. Okay, let's look at a fundamental theory of this, the beam theory. This show the Euler-Bernoulli beam theory, and this figure show the figure of Leonhard Euler and Daniel Bernoulli. That this kind of the two cases, mathematician that developed this kind of beam theory together. And what is the Euler-Bernoulli beam theory? The Euler-Bernoulli beam theory account only for the bending deformation that as we know. And the fundamental assumption of this beam theory, the plane sections remain plane and normal to the longitudinal axis. Okay, and this one show the kinematic description of the cross-section point for the Euler-Bernoulli beam. This one show the undeformed configuration, and this one show the deformed configuration. And U and V is a displacement field of this beam theory. Okay, and this one based on this figure, we have the displacement at a point with a distance y from the longitudinal axis. This one show the axial displacement field, and this one show the vertical displacement field. And these two displacement fields are derived based on the Euler-Bernoulli beam hypothesis. Okay, and this figure show the beam element that I will develop in this study. We have a 4 conventional beam decay freedom, and we have a 2 additional decay freedom that account for the strain gradient kinds of things. Okay, and following the sectional kinematic of the Euler-Bernoulli beam, we have a non-zero component of the strain tensor, and epsilon. We have this one is just a conventional strain tensor epsilon ij, and we have T kinds of gradient quantity. The first one is dilatation gradient vector, and the second one is the deviatoric stretch gradient tensor, and the third one is a symmetric curvature tensor. And all of these strain quantity can be described in terms of the beam displacement. Okay, and I show you the explicit form of the strain and the strain gradient measure. The first one is the conventional axial strain, and the strain in this box show the dilatation gradient, and the strain in this box show the deviatoric stretch gradient. Okay, and the third one is show the symmetric curvature. Okay, and to show its conjugate work pair, this one is show the conventional stress, and we have also the higher order state, and this one is the conjugate work pair of the dilatation gradient, and this one is the higher order state that is the conjugate work pair of the deviatoric stretch gradient, and this one is the higher order state that is the conjugate work pair of the symmetric curvature. Okay, and we will derive the governing equation within the framework of the virtual displacement principle, and this one show the virtual work equation. This one is show internal virtual work, and the last two terms show the external virtual work. Okay, and as I mentioned before, we will have two additional degree of freedom. This one I call the unconventional degree of freedom, because we have the higher order deformation mode to account for the small scale effect. Okay, and from the modified strain gradient constitutive relation, we have this kind of the virtual work equation. MC is the lower order moment, and this one is the kind of we call the resultant stress, resultant section moment, and this one is the higher order moment, is the kind of a higher order force that the conjugate work pair of the higher order deformation. Okay, then in order to have an Euler-Lagrange equation, we apply the integration by part. It applied twice to the first term and 3 times to the second term of this relation, and we end up with this equation. Okay, and due to the arbitrariness of the virtual displacement field, we have the Euler-Lagrange equation, and due to the arbitrariness of the virtual displacement at the end of the element, we have the classical boundary condition, and we have a non-classical boundary condition. Okay, and this one is only exists for the modified strain gradient theory. Okay, and for the compatibility equation, we have the curvature as the second derivative of the displacement, and we also have the curvature gradient because of the high order deformation due to the strain gradient theory. Okay, and this one shows the sectional force deformation relation. We have a lower order moment, and we have a curvature. This one is show the sectional stiffness due to the lower order moment. We have a non-classical moment, and we have this one is the kappa prime is the derivative of the curvature, and this one is the sectional stiffness due to the higher order deformation. Okay, and for the governing differential equation, we have this one. We put this equation together into this equation, and we have a governing differential equation in terms of the displacement field. You see, we have a 6th order differential equation instead of the 4th order as a conventional beam theory. Okay, and EIC is the sectional stiffness that belong to the lower order term, and EINC is the non-classical sectional stiffness that belong to the higher order differential term. Okay, and then we will start to formulate the finite element model based on this equation. Okay, and this one show the displacement based modified strain gradient beam element. Instead of having only 4 degrees of freedom as the conventional beam, we have 2 additional degrees of freedom at both ends of the beam. So we have the totally 6 degrees of freedom. Okay, and just follow the standard formulation step. We describe the vertical displacement field in terms of the nodal displacement that we have a 6 degree of freedoms. Okay, and then we can describe the curvature in terms of displacement to the strain displacement metric. Similarly, we can also describe the curvature gradient in terms of the nodal displacement to the strain displacement metric. Okay, and just put this equation into the virtual world equation. We end up with the finite element equation. We have 2 contributions. The first one is just like a conventional beam theory, and we also have additional stiffness metric term because of the strain gradient effect. Okay, then I will show you one example. I just finishing. I tell you the truth. I just finishing formulate this element, so I have only one example, and this one is this study. I intend to show you only the preliminary result of my study. Okay, for example, I have a cantilever beam. The length is 400 micrometer. And this the beam is made of the epoxy. This one is the material property of the epoxy. And this length scale parameter L0, L1, L2 equal to 7.6 micrometer. And this cantilever is subjected to the force at the force at the extreme end. Okay, and this one show the beam deflection profile, and this one is a conventional beam model. It's a classical beam model that we did not consider the microstructure effect at all. And the solid line here is the model that we developed here, and the dotted line another type of the nano beam theory, and they call the modified coupled state beam model. The thing that I found that when we account for the small scale effect, our response is show some stiffening effect, and this one is corresponding well to the experimental result on the nano side beam, and also corresponding well to the simulation that they use, they call the molecular dynamics kind of thing is in the physics field. I'm not familiar with that. I just found the result and compare it. Okay, and this one show the rotational profile of the beam. Okay, and this one show the curvature response, and all beam theory show the same displacement. All of the beam theory show the same bending moment diagram. Why? Because this structure is statically determinate. So the equilibrium equation mainly governed by the equilibrium. So either it not depend on the material model that you use. You should have a unique the equilibrium solution. Okay. And this one show the curvature gradient that you see the jump at the both end of the beam. Okay, and this one show the non-classical moment, the NC, MNC. Okay, and that is it. This is a very preliminary result that I got, okay? The conclusion and the future work that I will work on, continue on this beam theory. I formulate the higher order 6-order beam model that capable of accounting for the material length scale parameter. Numerical investigation show that the additional material length scale parameter are essential in describing the small side beam, both global and local response. And the next step that I will work on this beam theory, I will include the material and the material nonlinearity and the geometrically nonlinearity into this model. Okay, thanks for your kind attention. And this one show the picture of the real pool. I know that several audience from Europe, from England, so just want to show you that this picture of real pool. Okay.
Thank you, Professor Sunshar. It was a nice presentation. We have some time for questions. Do you have any questions for Professor Sunshar?
Yeah, please.
Anyone? So if no one has a question, I have just one question, Professor. I understand that your motivation is to model nano beams, stuff like that. But how this model compares to the traditional, the classical Bernoulli model in terms of, if you compare, for example, the experimental results from a nano beam compared with your model and the classical model, how does these results compare to each other? How better is your model than the conventional, the classical model? That's my question.
This one?
Yes.
Yeah. Okay. And this one shows the conventional beam model.
Okay. The classical one, yeah.
And it's more flexible.
Yes,
and
yes.
It's more flexible than our developed model.
Yeah.
And this finding is corresponding well to the, okay, they also carry out some experimental work on the small side beam. I don't know how they do it. I found in the literature, they say that when they test the very small beam, the structure will show the stiffening phenomenon. Okay. Yeah. I don't know. I don't know you buy it or not. Sorry.
Yeah, because it's very hard to believe that they can measure the displacement of a nano beam precisely.
Yeah,
you know?
yeah. I know. I tell you the truth. I really new to this field either, and I just want to try something new. I mean, I originally work on the earthquake engineering and kind of the fiber beam models, and I want to change, you know, to try something new.
Thank you very much for the presentation.
Yeah.
So I think you share the next, you introduce the next presenter.
Yeah, it's on my turn now, right?
Yes.
Okay. So the next presentation, the next speaker will be Dr. David Escolano Margaret, right?
Yeah, that's great.
Are you there?
Yeah, I'm here. Can you hear me?
Yeah, I see you. Dr. David Escalano is currently the assistant professor at the Department of Mechanical Engineering at the Polytechnical University of Madrid, right? Before, he was a Marie Curie Fellow at the University of Sheffield at the Concrete and Earthquake Engineering Group. He expertise the structural dynamics of concrete buildings, highly deformable rubberized concrete elements, and lately he working on energy dissipation device. Please, now the floor is yours. Thank you.
Can I share my screen? Or well, I think that you have to stop sharing your screen to allow me to.
Okay, I'm sorry. And let's see. I have to stop first, right?
Yeah.
Yeah, sorry. Let me give me a minute. Okay. Stop now, right? So you can only see my face.
Can you
Stop now,
see
right?
my screen now?
You starting yet?
Yes.
Yeah, I see your conclusion. You jump to the conclusion.
Well, no, yeah, just like.
Oh yeah, okay. Thanks.
Oh, okay. Sorry, just a second, because I'm sharing the wrong screen. Sorry.
All right.
So can you see now? Can you see my presentation now?
Yes, yes.
All right. So first of all, I would like to thank Dr. Tanosa for inviting me for this really interesting symposium. And I really need to apologize to him because I was late this morning because of I messed up with time. So I missed the first few presentations which I was supposed to share. So really, I'm really sorry for that. Anyway, today I'm going to present my very last work that we've been doing here in Polytechnical University of Madrid. We're working now in using energy dissipation devices, which are metallic devices, to do seismic protection of buildings. So my presentation, I will start introducing, which is our new development, a tube-in-tube damper, and then I'll show you some results from the experimental investigation we did on shaking table tests. So our damper is basically a metallic damper, which is a energy dissipation device, which is dependent on the displacement, and it relies on the deformation or the plastic deformation of these elements, which are little like slits that we do in a plate. So basically, the plastic deformation of these elements is what is providing the energy dissipation when an earthquake strikes our building. So this configuration is our tube-in-tube damper. Basically, it's like two hollow sections, square sections, one inside the other. And we have the outer section, the outer tube is slit in this sense. So what we essentially do is we weld the outer tube with the inner tube through this button welding. So when the earthquake strikes, it imposes an axial deformation in this thing, and it forces a deformation, a bending type of deformation in the tube. So how is this energy damper supposed to work in a structure? So essentially, we put it like a diagonal brace. So it's essentially like a diagonal brace, which is engineered to concentrate all the damage in our energy dissipator. All right. So we fabricated several prototypes of this energy damper. We place it in a reinforced concrete structure. This reinforced concrete structure was basically a part, because our shaking table is quite small, but we designed a reinforced concrete structure. We built a little part of this structure. We did like 1.5 bays and 1.5 stories. And then we replaced the rest of the structure by reaction blocks, which are basically forcing inertial forces in our structure. Here we can see the shake table test, like the schematic of the setup, and this is a picture of the setup. Let me move to a video. Can you see the video? So basically, this is the test we did. So you can see that the shake table was imposing a 2 degrees of freedom earthquake. It was an Italian earthquake. And we have these two actuators which are like imposing the acceleration which were recorded in the Campano Lucano earthquake of Italy. we can see also if we focus on the device, we can see how this device works. So in the diagonal, we can see that it was moving and then reinforcing the deformation in our energy dissipation, in our energy damper. So you can see here how these slits, these little beams, are deforming, and it's basically concentrated all the damage that we have in the earthquake. So we can see in this bottom plots, we can see the hysteresis loop that were recorded in the damper. So basically, it's like the actual deformation against the actual force that was measured in each of the dampers that we place in the structure. After we did the test with several intensity earthquakes, we found out that the dampers, they were not fully utilized. So we move it into another test. We took these dampers from the structure and we placed it in a universal testing machine. We did this because we wanted to know the final energy dissipation capacity at failure of our dampers. So after the shaken table test, we did some quasi-static tests until we reached the failure of our damper. With these hysteresis loops, basically what we did is quantify the energy dissipation capacity of our dampers. To do that, we use a very old theory. Well, it's a theory from the 80s from a Japanese professor, Hiroshi Akiyama. And we basically took the hysteresis loops and we divided it in two parts. The skeleton part, which is basically all the branches of the hysteresis loop that exceed the force or the maximum force in a previous loop. So it would be like branch 0 to 1, then 4 to 5, then 9 to 10 to 12, and then we put everything together, right? So we can build a skeleton which is very close to the static skeleton of our damper. The other part could be the energy dissipating in the Böshinger part, which is all the branches that didn't exceed the maximum deformation in a previous loop. So by dividing our hysteresis loop in these two parts, we can obtain the energy dissipated through the skeleton and the energy dissipated through the Böshinger effect. This is like very typical in steel structures, so we can see this kind of analysis in beams and many other metallic compounds. So this energy can be also normalized through the yielding displacement and the yielding force. And this is what Akiyama called the cumulative energy dissipation ratio. Why we want to compute this cumulative dissipation ratio? Because based on the results on the energy dissipated on the Böshinger part and the energy dissipated in the skeleton part, at failure, we can find these three experimental points and these three experimental points. Here we can see the energy dissipated in the Böshinger and the skeleton part against the ductility. And this allows to define this failure curve that defines the exact moment that our damper will fail. Considering the energy dissipated in Böshinger and the skeleton part, we can build a failure envelope. With this failure envelope, what allows us is no matter what the load part we have in the damper, and no matter the situation that of loading and displacement, we can predict when it's going exactly to fail our damper. So that's the magic of this thing. If we can somehow instrument our damper and then know the displacement history of our damper, we will know how much was damaged and how extra energy we have to resist an earthquake. So in this sense, we can predict numerically which would be the energy dissipated on our damper, and we can know numerically how much do we have or how much energy we need to reach the failure in our structure. So here we can see the prediction or the experimental work done with obtained during the quasi-static test and some models that we did with OpenSys. These models, you can see that the prediction of the energy path is dissipated in the Bausinger part and the skeleton part is very close, and we can predict fairly accurately the exact point in which our damper will fail. So moving to the conclusions, we can say that the TTD damper or the tube-in-tube damper is a fairly stable energy dissipation device with really nice and stable hysteretic behavior that allows to dissipate large amount of energy per cycle. It presents a ductility around 12 and 15 before we have a second order effects, large strains effects, and we can show that the energy dissipation capacity for our damper can be predicted by numerical model, so we can fully know how much energy will allow our TTD damper to dissipate in an earthquake. So thank you. I was fairly brief, but because I think that it was to allow some time for questions. So thank you very much. And if you have any questions, I will be very happy to take them.
Yeah. Thank Davis for your very nice and clear presentation. Any question from the audience? I think we have time, right?
Yes, we do have time because this is the last day.
Yeah, we have till midnight. Yeah. Yes.
Please.
So I have a question.
Go for it.
Excuse me, in the third page of your presentation, in one of the hysteresis loops on the right hand, there is a shift to the right hand of the, on the right hand of the hysteresis loop, and I want to know what is the reason for that shift to the right hand. There is not a symmetric loops. I think it was in the third page of your presentation. If you
mean this one?
Bring that page. No.
Third page. Okay. This one? This shift of to the right.
Yes, yes.
Yeah,
I want to know why we have because I think because of some plastic deformations, maybe.
Well, this is the damper that was placed on the top, on the very top.
Yes, yes, this page, I mean, exactly, yes.
Yeah, so yeah, basically in the shake table test, the Campano-Lucano earthquake has a very high stress peak. So it was like a very large push in one direction. So the columns on the top, they basically suffer some plastic strains, like very large plastic strains in this like push. So basically the top story was like leaning on that direction. So the rest of the loops in the earthquake were just like pushing in this direction with a plastic strain already happened in the columns. So that's why this looks this way. In the bottom part, it had like a much better behavior. So basically, the columns behave in the elastic range, and the dampers were like protecting the structure fairly well.
Okay, thank you for your explanation.
Thank you.
Yeah. Okay. Any more? Some more.
I have a very simple question. Hi, David. Very interesting presentation. I just wasn't sure or clear on how you connect the damper to the bracing element, and then you force that deformation of the fins.
Yeah. The damper. Well, we have this diagonal, right? So the inner tube is connected to this brace, and the outer tube is connected to the other connection here. So basically, we are imposing. You can see in the video. You can see it here that the outer section and the inner section are connecting to different parts of the braces. So we are imposing an axial deformation within the two tubes. That was your question, Mauricio, or not?
Yeah, I wasn't just sure how you can, because it looks like they're deforming in, so the fins are deforming in bending, which means you put shear on the damper.
Yeah, that's the thing. So
it's connected on one side.
The outer tube, you can see here,
yes.
The outer tube is connected to one side, and the inner tube is connected to the other side. So
but you force the deformation of the fins.
The formation of the thing is like this. It's like induced by shear deformation, but with bending in these little strips. So the energy
it's only connected to one side.
So the energy dissipation occurs on the extremes of these little thin strips.
Yes.
We have
I see now.
So we are restraining the thing in the position of shear deformation, forcing a bending force. What happens is that if large deformations occur in these things, we have things like this, that is second order effects, because we have geometrical second order effects. So we can reach ductilities around 12-15 before these like sudden second order effects we have. But that is because we are imposing this thing, and these plates cannot allow deformation in the X direction. They can allow only Y direction deformation. And it's a fairly good energy damper up to that point that the second order can kick in, and then it can impose like very, very large forces in our structure.
Yeah, thank you.
Professor Suchard, can I ask one question? Okay.
Yeah, go for it.
Well, this is Penning. I'd like to ask a few questions about this type of damper. I think this is a kind of a metallic hysteretic damper, and there are actually many types of metallic dampers. So what is a special advantage of this type of damper? Do you have any clear reason why we have to go with this special design in this configuration?
Well, yeah, I mean, it's the difference with other dampers is like we kind of maximize the amount of strips that they can provide energy dissipation in the structure. It's also I forgot to mention, it's a stainless steel damper, which is like it has